Good morning, everyone, and welcome to the third Shared Water, Shared Future workshop, Utility, Climate, and Drought Preparedness. Thank you for deciding to spend your morning with us. My name is Kate Avasik, and I lead the Climate Resilience and Water Program at the Chicago Metropolitan Agency for Planning. And I'm especially excited about today's sessions where we're going to dig into the data, tools, and other resources available to help utilities and communities plan for drought and future climate conditions. Today's workshop focuses on increasing water system resilience, but we know that we need action to reduce greenhouse gas emissions from the water sector as well. The AWWA M71 manual, which you'll hear about a little bit later, delves into both climate resilience and climate mitigation for the water sector. But I also wanted to mention that we have a bold new plan called the Comprehensive Climate Action Plan that shows a path to dramatically cut greenhouse gas emissions across the greater Chicago region, including within the water sector. So I encourage you all to check that plan out through the link provided in the chat. So we're going to kick things off this morning by learning a little bit about who you are. So please use the chat to share your name, your title, and your organization. And then while you're entering that information, I'm going to share a little bit more about the workshop series. Shared Water, Shared Future is a five-part virtual workshop series designed to bring people together to address the pressing water supply issues of Northeastern Illinois. As many of you know, our region depends on shared water resources that cross community and county boundaries. While Lake Michigan, the Fox and Kankakee rivers, and groundwater aquifers all currently provide clean water, their capacity to serve our needs is not limitless. To secure a reliable and sustainable water future as our region grows, communities, utilities, and organizations must all plan ahead, coordinate across boundaries, and adopt conservation strategies. Through interactive sessions, expert presentations, and collaborative exercises, Shared Waters, Shared Future will help us all gain actionable strategies and planning tools to improve water management and efficiency. This series is hosted by CMAP in partnership with the Illinois-Indiana Sea Grant and with support from Illinois Department of Natural Resources, Office of Water Resources. And my colleague, Margaret Schneemann, with the Illinois-Indiana Sea Grant, has really been instrumental in pulling together this workshop. And so I'm going to hand it over to her to provide a little bit more information on Shared Water, Shared Future and introduce our agenda for today. So thank you.
Great. Thanks so much, Kate, for the introduction. So today's session is the third workshop in a five-part series. We have already held our first two workshops in February and April, and we have two more planned this year in September and November. And so our last workshop focused on water supply sustainability planning. The workshop recap, recording, and materials are all available on the Shared Water, Shared Futures website, so be sure to check it out if you missed it. So we're very excited for today's workshop and our fantastic lineup of speakers who will help us explore, as Kate mentioned, climate and drought conditions, how they translate into practical planning, preparedness, and operational decisions for community water suppliers. As Kate mentioned, we'll be using Mentimeter polling software throughout today's workshop. So please, if you can, go ahead and click on the link in the chat, or you can use your phone to scan the QR code that's on the screen. Once you're in, please do keep the Mentimeter polling software open, since we'll come back to it several times throughout the course of the workshop. If you have any trouble accessing the Mentimeter software, please let us know in the chat and we'll do our best to assist you. So to get us started, we'd like you to choose the option that best describes your primary role. Are you a local government staff or elected official, water utility staff, a consultant or engineer? Are you with a nonprofit or advocacy organization, a regional planning or technical assistance organization, in research, in academia, or in some other role that we haven't mentioned? And if you are in some other role, we'd love to hear about that in the chat. Okay, so I'll give people a little bit of time to join and vote. It looks like folks have started voting already, and we're seeing a mix of people from local government staff, other organizations, regional planning. So it looks like we've got a pretty good mix of people. Okay, we have 16 out of 24 responded, so I'll give it just another second. Okay, so next we'd also like to learn a little bit more about what brought you here today. You should see an open-ended question asking, why are you attending today's workshop? So whether you're looking for practical tools, planning strategies, general climate or drought information, or you're simply just trying to learn more about the topic, we'd love to hear what motivated you to join us here today. So even just a couple words is fine. Maybe it's a specific challenge you're facing, a question that you hope will get answered in the workshop, or something you're hoping to take back to your own organization. Okay, so far it looks like people are hoping to learn more about the topic in general. To get new ideas, to keep up with current issues, to help with planning, to expand your knowledge base. Okay, thank you all so much for sharing those answers. Finally, we are curious to know about what climate hazard is your community water supply system most impacted by. This one is multiple choice. You can choose flooding or heavy precipitation, drought, severe storms, extreme heat, extreme cold, freeze-thaw cycles, other, or I don't know. And if you do select other, feel free to share more about that specific climate hazard that your community is facing in the chat. Okay, it looks like flooding is coming up as one of the top climate hazards people are facing, followed by drought. Okay, great. Thanks, everyone. Those answers really give us a helpful context for the range of experiences and concerns that are represented here today and informing what we're covering today. So moving on to our first session. Our first session does focus on understanding the climate and drought information that can support water supply planning, preparedness, and decision making. And so before we go any further, we do have one more quick set of poll questions for you. Hopefully you do still have the Mentimeter software open, but if not, or if you just joined us, please read or join the QR code on the screen, the link in the chat. Because we do have participants joining us today from a variety of backgrounds and organizations, we're curious to learn a little bit more about your experience with today's topic. And so our first question is, how familiar are you with drought monitoring tools and resources? Would you say that you're not at all familiar? Are you slightly familiar, moderately familiar, or extremely familiar? So please select the answer that best reflects your current level of familiarity with resources. Okay, it looks like most people so far are moderately familiar with the resources, followed by slightly familiar, and then a mix of people that are not at all familiar and very familiar. Okay, thank you for sharing that. Let's move to the second question, which is also open-ended. We are curious to know, in your experience and opinion, in what ways do you think climate and drought conditions affect water supply? Again, feel free to share just a few words, a specific example, or a challenge that you've seen in your community or utility. And this one is open-ended. Okay, there's no right or wrong answers here. So anything you may have seen. Okay, freezing of water intake pipes from Lake Michigan. Hmm. Accelerating drawdown in aquifers. General limits on supply. Combined sewer overflows. Extended droughts. Increase in irrigation demand. Decreasing groundwater levels affecting pumping. Too many ways, and knowledge is power, and that's why I'm here. Increased demand while lower source storage. Drought, heavy rain, lots of flooding. Okay, great. Thank you all for sharing your perspectives on that. We will be revisiting many of these ideas throughout today's presentations as our speakers explore how climate and drought conditions affect water. And so moving on to our first session, we have 3 great talks in this session. So we'll hear about what is drought and how we monitor it, what climate information is available and how do we use it, and what does this look like on the ground for a groundwater dependent community. We'll begin with our first speaker, Molly Wolozin from the National Integrated Drought Information System. We'll then hear from Illinois State climatologist Trent Ford and Scott Kuykendall from McHenry County Planning and Development. So our first speaker is Molly. Molly is a senior associate scientist with the Cooperative Institute for Research and Environmental Sciences at the University of Colorado Boulder. She serves as a regional drought information coordinator with NOAA's National Integrated Drought Information System, and she's the program point of contact for the Midwest Drought Early Warning System. She's located here in Champaign, Illinois. And as a reminder, we'll be sharing all the presentations and resource links after today's workshop that Molly and the other speakers will be mentioning. We'll just be dropping a couple critical links into the chat if you want to check those out during the talk. Please do feel free to put any questions you have for Molly into the chat as they come up, and we'll be addressing those questions at the end of her talk. And with that, I'll turn it over to you, Molly.
Great. Thank you so much, Margaret. I'm really excited to be here today. Thank you again for the invitation to present about drought, specifically in Northeastern Illinois. And I'm excited to be at this workshop. My past life, I was with Illinois Indiana Sea Grant as a climate specialist. So it's great to be here. Next slide. Drought is one of the most expensive natural disasters, but its impacts are much more complex than just a dollar figure. It leads to a wide array of environmental, social, and economic consequences, and those can range from lower water levels that impact shipping to agricultural losses and water supply issues. And I know drought in an urban area is a little bit different. You might not feel the impacts as much for people that are living in urban areas, compared to those that are living in more rural areas. So I did want to highlight some of the more common impacts that you might feel in northeastern Illinois from drought. So, of course, water vulnerabilities can be an issue, whether you're talking about surface water supply or groundwater. Urban forests and vegetation stress is often an issue that's experienced. Also, heat and drought and the combination. Often, drought can be exacerbated by heat. There's foundational issues, air quality, wildlife impacts that you can feel in an urban area. And the occurrence of drought in northeastern Illinois definitely has fluctuated over the years. And of course, over the last few decades, there has been more of a wetting trend. You've seen a lot more precipitation, heavier precipitation, and you're often dealing with flooding issues. But drought has also been an issue, specifically back in 2005 was probably the last widespread severe drought. So I'm not sure if anyone was around and managing drought in this area during that time. But even in more recent years, we have had some pretty severe drought conditions in the northeastern Illinois area. Next slide. So, drought in the simplest form is just the lack of precipitation over an extended period of time that results in some sort of impact. I don't want to make it too complicated, but I did want to point out that there are different types of drought. So, if you're looking at just the dry weather, that might be referred to as a meteorological drought. But where the impacts come in are really when we start to see those impacts to agriculture. So, agricultural drought is when our crops are impacted by dry weather. Hydrological drought is when we start to see those impacts to different types of water supplies, whether that's groundwater, surface water, stream flow. And then there's also ecological drought, which is when drought impacts ecosystems. And of course, all of these are tied together, but the reason that there are differences is that there might be different data sets that you use depending on what you care about. And so that's really what I wanted to highlight here is just the use of different data sets depending on what you care about is. There's also flash drought, which I'm not sure how familiar all of you are with that terminology. But this is something that is fairly common in the Midwest, which is the rapid intensification of drought conditions. So, flash drought often happens in the summer months when we maybe stop receiving precipitation and then also can see an increase in high temperatures. And we're actually experiencing this and seeing some flash drought develop in your area, northern Illinois, up into Wisconsin and Minnesota right now with the hotter temperatures and the drier weather that's been the pattern for the last week or so, and it's forecasted to continue for a bit. So again, there are different types of drought and the data sets vary. And if you want to move to the next slide, this shows another graphic looking at some of the different data sets that you can look at to track drought. And so you often are using a variety of different data sets and indicators ranging from, of course, precipitation, but other variables, looking at how groundwater is reacting to drought, how soil moisture is reacting, what is the vegetation health, what are the stream gauge levels, the stream flow? What's evapotranspiration, which is when moisture is extracted from the surface from high temperatures. So there is a lot of data that can be used, and I'm hoping to provide you a little bit more information today on where you can go to get this information. And then, of course, Trent and Scott will also provide you more information as well. Next slide. So, before we get into exactly where you find the data, why is it important to have accurate drought monitoring and assessment? Really, having accurate drought monitoring and assessment and being aware of the conditions in your area can really play an important role in supporting your community and other in your sectors that you care about to prepare and mitigate and respond to drought. So it helps identify which areas are most vulnerable, so that can allow for more effective and targeted relief efforts. It also can allow for precise monitoring can allow for faster and more effective response, especially if we are in a flash drought and decisions do need to be made fast. And if you are looking at the data and understand where you're at, you'll be able to make those decisions more quickly and more effectively. And also, if you have inaccurate assessment of drought, that can actually lead to economic inequities and maladaptation. So, really understanding where you're at in drought and what your historical record is and how that compares to normal is important in your response and management of drought. Next slide. So I'm going to talk about some drought monitoring resources, primarily from drought.gov, and then also at the very end talk with you a little bit more about the program that I work for, NIDIS, and how you can get more engaged within the Midwest network that we have here and what exactly that means and what value it might bring. Next slide. So, NIDIS hosts the U.S. Drought Portal, or drought.gov, which is the U.S. government's authoritative drought information website. So, NIDIS, it has a public law mandate from Congress, and we've been around for around 20 years. And within the last few years, we relaunched drought.gov and really view it as a one-stop shop for a lot of your data, decision support products, and resources around drought. And we really tried to make it in a way that it's interactive and customizable to your needs. Just looking at some of the statistics for the Midwest use of drought.gov, we have state pages, which I'll highlight here in a second. And, we have pretty frequent traffic, especially obviously when we're in drought. And also, we release drought status updates, which are used from partners and stakeholders across the region. Next slide. So highlighting the Illinois state page. So we developed all of our state pages in consultation with state partners. In the case of Illinois, we worked really closely with Trent and the Illinois State Climate Office to develop this page. And we, on these state pages, provide access to a variety of data sets and products, but also point you to the state government drought resources. So that little box on the far right, it provides you access to relevant information for your state, like from the Illinois State Water Survey, from Trent's shop, the state agency of DNR and their water supply page, as well as the drought plan. So you can get a lot of information about the state as a whole on the Illinois state page. And from the state page, you are able to drill down into other scales. And if you want to move to the next slide, this page really focuses on showing you that on drought.gov, you can drill down to your local scale. So you can go from the global scale to the US to regional, state, county, and local. So if you are on the main page of drought.gov, there is a by location tab, and on that you can then go to various scales that you want to look at. And there's a lot of information available on these local pages. I know most of you would probably be interested in the county or local pages. So we have access to the U.S. Drought Monitor, the population in drought, precipitation and temperature, as well as records that you might be experiencing. And then other data sets like stream flow, soil moisture, the air quality index, and agriculture in drought. We also provide access to the outlooks. So if you're looking for information on, 1 day or 7 day precipitation, as well as what the outlooks are showing for the next month or season. And there's also some really neat historical tools as well. So you can look at historically the U.S. Drought Monitor, as well as even going back to the late 1800s. And we even have paleoclimate data, which is kind of interesting to look at as well. So I definitely encourage you to go to the by location page and drill down to your local scale. And I'm always open to hearing feedback if there's something that's not on the page that you're looking for. We're always looking for ways to improve drought.gov. Next slide. There's also another way that you can directly receive an email if you want when drought conditions change or when conditions are expected to change. So we do have ways that you can get local drought alerts. So if you are on any page on drought.gov, and you click on the sign up for alerts, and it looks like it just was put in the chat box as well. So thank you for that. You can sign up for alerts when the drought monitor changes categories, whether that's improve or worsening. And then also if the U.S. drought outlooks from NOAA for the 1 or 3 month drought outlooks show that drought is expected to develop or improve, you'll also get an email for that. So the bottom left there is showing what the email looks like when you receive an email. So it's a really user-friendly way to stay up to date to your conditions if it's something that you want to proactively receive as opposed to having to go seek out the information. Next slide. I did want to briefly talk about the U.S. Drought Monitor. That is, the kind of golden standard of what we use for drought monitoring. If you want just a snapshot of what drought conditions are, this is often the map that people use. So I did want to tell you a little bit about how it's made because it's really Trent and other state offices are very involved in trying to make this an accurate map. So the U.S. Drought Monitor is released every Thursday showing where drought is and how bad it is across the country using D1, which is moderate drought, up to D4, which is exceptional drought. And there's also a category of D0, which is abnormally dry. That's not technically drought. That means we're either going into drought or could be going into drought or coming out of drought. So that's kind of the last category before an area is shown as white or no drought. So the U.S. Drought Monitor is created by a national author every week, and they are using a variety of data sets from observational satellite model data sets for a lot of indicators. So they're taking precipitation, soil moisture, stream flow, a lot of different data sets to create this map, and using the convergence of evidence approach. So there's different percentiles that are attached to it, and they are coming up with a recommendation for what the drought level should be. But what's really key here is that there is a network of people that provide input from state and local teams, based to ground truth the data. So, like I mentioned, the Illinois team is led by Trent, and there's a lot of other people that are involved in making recommendations every week into the U.S. Drought Monitor. But they are essentially taking the data sets and the local data that we have here, as well as reports from people across the state to see how well does the data match up with the impacts? Do we need to make adjustments based on that? So having that local information across the state is really important for an accurate U.S. Drought Monitor map. And why that's important is that USDA does use the U.S. Drought Monitor as a trigger for drought assistance programs. And also, state agencies often use the U.S. Drought Monitor for drought declarations to trigger state relief actions. So it is an important map to get right. So if you could move to the next slide. I did want to make a plug on a way that you can help, if you're interested in having those on the ground reports. Like I said, it's really important that we know what's going on across the state because obviously one person is not located across all areas of the state. It's impossible to know what's going on. And so it's important to have those reports from people. And so there are ways that you can report your local drought impacts through two different systems. One of them is called CMOR, which is the Condition Monitoring Observer Reports. And that's a system for anybody to go report their conditions. And you can actually, it's most valuable if you report on a regular basis. And you can also report when it's really wet to really dry. So I can put the link in the chat box here, if you're interested in doing that. But again, you can put commentary, mark different impacts that you're experiencing. You can even include a photo, which is really helpful as well. If you are a CocoRa's observer, which I'm not sure how many of you are familiar with CocoRa's, but it's the collaborative, I know I'm going to struggle on this, Community Collaborative Rain, Hail, and Snow Network. But there is a way to submit condition monitoring reports through that portal as well. So again, I will put the link in the chat box here, in just a second. Let me try to double task for a minute. And if you're interested in providing your impact reports, that would be very helpful. Next slide. So I wanted to finish here with just a few slides talking to you about NIDIS, which is the program that I work for. We are located within NOAA, the National Oceanic and Atmospheric Administration, but we do have a mandate from Congress. We have a public law, and we've been in existence for about 20 years now. Actually, this year is our 20th anniversary. And one of the ways that or our mandate from Congress, we are a multi-agency partnership that coordinates drought monitoring, forecasting, planning, and information across the country. Our overarching goal is to help our country move from a reactive to a more proactive approach to drought. And a lot of the work that we do is through our regional drought early warning systems, or DEWs. And I coordinate the Midwest region, which is shown in brown on the map. And so the regional DEWs are one way that we really amplify the work across the region. We also work on improving drought prediction and forecasting. We support planning and preparedness, and again, also deliver information through drought.gov. Next slide. So what is a drought early warning system? It helps improve the capacity of farmers, ranchers, water suppliers, any other decision maker to help them plan for, forecast, monitor, and cope with the impacts of drought. And really, this is accomplished through a network of partners that are working together to help prepare the different regions for drought. For the Midwest, our partnership has been around for about 10 years. We've had the regional DEWs, and we have a pretty active, robust network of people that are sharing information, working with one another to help improve our preparedness for drought. Next slide. So here's a few different ways just to kind of tangibly show you what a Midwest Dues looks like in action. So we provide forums for sharing information and experiences with managing drought. We do have in-person meetings, but we also have virtual engagements. In the past, I've convened virtual engagements around drought planning, soil moisture data, and other drought indicators and other efforts. We deliver information through newsletters, drought status updates, webinars, drought.gov, and I'll show more about that on the next slide and how you can stay in the loop. One of the key things, though, from a regional dues and the Midwest dues in particular, is we document the gaps, needs, and opportunities that are identified by partners across the region. So through our in-person engagements or virtual engagements, we listen to people that are managing and responding to drought and hear what the needs are. Do they have access to the data that they need? Do they need to know how to even start writing a drought plan? We document those needs through our strategic plans, our meeting reports, and we try to advance those efforts together as a network. And also integrating the latest science as well to help us inform decision making. So the network of partners is made up of a lot of different entities, state and local agencies, drought monitoring teams, federal agencies, private sector are just among the groups of people that are involved. Next slide. So if you're interested in staying up to date on drought conditions in the Midwest, we do release drought status updates and we also have webinars. We actually have the next one tomorrow at 2 p.m. Central if you're interested. So we try to provide information on the conditions, the impacts, and also the outlook. So trying to make it fairly concise and usable within these different avenues. And next slide. So that is all that I have. And I will put the link again, it's the sign up link in the chat box. If you are interested in staying in the loop on efforts for the Midwest, you can go to that link. And if you scroll down to regional mailing lists, you will see an option for the Midwest, and you can subscribe to that or any other regions that you're interested in. But I'm happy to take any questions or make any clarifications. Thank you.
Great. Thanks, Molly. That was a lot of helpful information to help us better understand drought monitoring, all the factors that contribute to the development of drought, and all the tools and resources and assistance that's available for us. So we do have a few minutes for questions. So if you do have a question for Molly, as a reminder, please feel free to enter into the chat. And we'll look to see if any questions came in. In the meantime, Molly, I have a question. You mentioned flash droughts and that we are currently in a flash drought. I'm wondering how much warning do communities typically have before a flash drought occurs, and what makes them particularly challenging to monitor and respond to?
Yeah, that's a good question. So flash drought, right now I would say, because if you look at the map, there actually is not drought on the map. But what it is that the conditions are right for us to see rapid intensification. So if this pattern continues with dry weather, warmer weather, we could see drought develop. And so flash drought is challenging because it might develop over the course of a few weeks, which usually, our tools and data that we're using for flash drought are getting better. We have more tools available, but usually it's a few weeks, but you might not be feeling the impacts yet. So of course, it might take time to feel those impacts if it persists. But I think it's just the point that it's good to be aware that it can develop quickly and therefore something to look out for, because what's challenging is you have less time to respond. Um, of course, with flash drought, you likely will not be experiencing water supply shortages right off the bat. Those conditions would have to persist for most water supply entities. But of course, with agriculture, you can feel the impacts quicker, vegetation. So there's other, ecosystems often could feel the impact of flash drought on, more quickly than others. So hopefully that answered your question. But usually they develop over the course of a few weeks. And then again, if that persists, then you might see drought impacts.
Okay, great. Thank you so much. So another question is, we've had collaboration be like a huge theme for our workshop. So I'm curious, if you can share an example of how the types of collaboration you've been talking about within the Midwest Drought Early Warning System has improved drought monitoring, preparedness, or response.
Yeah, I can share one example that comes to mind is a couple of years ago. Well, I guess I should say something that we do on an annual basis now and have for the last 3 years is that I host a virtual meeting every spring around the early April timeframe where I invite the drought monitoring teams from the states to come and talk about the conditions, what concerns they have for the upcoming growing season, what the outlooks are showing us. And that can help us with our regional messaging around drought. And so a couple of years ago in 2024, we were actually looking pretty good. There was a lot of spring rain, but we could see that because of some of our longer term deficits, if we got dry and had those high temperatures, we would get drought development pretty quickly. And so we did release some regional communications about that, which then the Ohio State climatologist had used to kind of move forward some extension resources to compile information about drought. And then Ohio did actually get really bad. They reached exceptional drought on the U.S. Drought Monitor, which was the first time since the Drought Monitor had have has been in existence. So it helped enact some actions on the ground in terms of providing resources to producers and farmers and water suppliers. So that's sort of the messaging and delivering of information that, the network together is trying to use in order to improve drought response. So that's just one example that I can think of. But there's a lot of other, a lot of states are like Trent is a prime example of someone that's great at monitoring drought, and we have convened as a group to learn from one another on how do you accurately assess drought? What are the best data sets for the region and trying to learn from one another, and that's helped efforts in other states as well.
Okay, great. Thank you so much, Molly. That's all the time that we have for questions right now, but thank you for sharing all your expertise with us, Molly. We really appreciate you being
Yeah,
here today.
thank you.
Our next speaker is Trent Ford. Trent is the Illinois State climatologist and has been with the Prairie Research Institute at the University of Illinois since 2019. He's an expert in climate and climate change and its interactions and impacts, especially as they relate to water. Trent leads the climate and drought monitoring research and data collection for Illinois. Him and his team work with communities, industries, and state agencies on issues related to weather, climate, and climate change in Illinois. And they engage the general public through online media and educational outreach. A native of Roanoke, Illinois, Ford earned a bachelor's in geography from Illinois State University before completing his master's and PhD at Texas A&M. So please join me in welcoming Trent Ford.
Yeah, thanks, Margaret. Appreciate it. And thanks for the opportunity. You can go to the next slide if you want. So normally when I'm talking, and I going through the names of folks on here, I recognize a lot of folks, and good to see everybody again. Usually I'm talking about all the terrible things that climate change has brought or will bring. Today, I get to nerd out about climate data. So kind of following on what Molly talked about with resources available for drought monitoring. Specifically, what I'm going to talk about is resources, information, data resources for preparedness and assessment. So it can be for planning purposes or just to answer a question of how often have we been this dry or this wet, that sort of thing. So we'll go through some of the ins and outs of different types of climate data sets, including at the end climate projections. So go ahead and go to the next slide. Okay, so we're going to start in the past and then we'll move to the future. So all of this will make sense of the timelines. We're going to talk about how to some of the my favorite resources for getting past weather and climate data. Go ahead and go to the next slide. Okay, so weather station observations are the gold standard of weather observation, obviously, but also drought observations. And weather station observations have the benefit of, in many cases, having decades, if not over a century worth of at least daily weather observations. In fact, I just this morning wrote a letter of recognition to somebody who has been monitoring daily weather for 70 years, going out every single day for 70 years in the Chicagoland area to write down how much precipitation their station received and what the temperatures were. So that is a critical source of information to understand all of the things about climate change that I often talk about. Now, the part of the National Weather Service runs thousands of stations all across the country that are monitored by volunteers, like I mentioned, the guy that I mentioned earlier, um, measuring daily temperature, precipitation, in some cases evaporation, wind, humidity. Like I mentioned, some of these stations have been operating since the late 1800s. Some of the data we can get from the Chicagoland area go back to the mid 1800s. The ideal use of this data, as most of you use it often, is to monitor weather, understand past conditions, what your normal is, what the expectation is, and what the extremes are. So if you're using any estimate of a 50-year drought, Q710 for stream flow, the 1% annual exceedance probability rainfall event, all of those things are primarily based off of these direct weather observations. And because we have those decades worth of consistent measurements, we can also measure change in all of those, which is really critical. So these data sets are super important and the for best place to start for understanding variability and then quantifying risk. Now have two big asterisks there next to quantifying risk. This is all past risk. So if you're using weather station observations to, for example, estimate the 1% annual exceedance probability storm for a 24-hour period, and you use the last century or so of observations, that's going to quantify the risk or the probability for the last 100 years, not the next 100 years. So we'll talk about future in a little bit, but I wanted to just put that out there. Two of my favorite sources for past weather information are the ACIS, Applied Climate Information Services or System data set. XC ACIS is a sort of GUI-based web page that is pretty straightforward to go through. And to look to do all sorts of interesting types of breakdowns of climate data. So you can search for the Chicago region, which of course is represented by different stations that is currently O'Hare, but has moved around the region for the last 134, 140 years. And then the Midwestern Regional Climate Center, which I see is the link is already been posted there. They have revamped their what they call Climate, which is their data services portal, to be quicker and much more user friendly. And the key about the Midwestern Regional Climate Center data set is that they have hourly data. So if you're looking for something of just like how much precipitation you get in a day, in a season, in a month, in a year, in a decade, whatever that may be, the ACIS or XC ACIS is a great resource. If you're needing hourly observations, weather observations for extreme heat analysis, like heat index, for hourly precipitation, those kinds of things, the Midwestern Regional Climate Center is a really, again, user-friendly, quick resource. And so I have a bunch of QR codes throughout these slides. Here are two of them here, just so folks can play around with those systems. And although most of these systems are pretty self-explanatory, especially if you have some kind of working knowledge of climate data, I will say, and I think I have my contact information at the end, and certainly it's blasted everywhere. If you are going through any of these systems and run into problems, questions, just barriers, whatever it may be, something's not working right, definitely don't hesitate to reach out to my office to ask for assistance. We're always happy to help with getting people the climate data they need. Go ahead and go to the next slide for me. So this is a list. Don't write these down furiously. CMAP has my slides, so hopefully they can send those out to everybody on this call. But here's some other weather station data access points. Notice I have XMASIS and MRCC, the Midwestern Regional Climate Center, up at the top. The reason I have those listed up top is because they are the powerful and in my opinion, the most user friendly. However, there are other very powerful, very useful portals or access points for data that may be a little bit of a larger learning curve, but once you get that learning curve, they're super helpful. The Iowa Environmental Mesonet, don't let the name dissuade you from going there. They have data for all across the country, not just Iowa. Of course, the National Centers for Environmental Information, NOAA. I've learned through my years as state climatologist not to make the mistake of just sending somebody to a random NOAA website because they'll be lost into the void forever. So we have specific ones here for NCEI. And all of those three are repeated, which is really exciting. So I love them so much. I repeated them twice here. So things to remember about using National Weather Service weather station data. Data are specific to a single station. For temperature, not that big a deal. For precipitation, big deal. So if you are trying to represent what the 1% annual exceedance probability storm is, what the return period on some value of drought is for the entirety of Lake County, if you're using one station, let's see at Waukegan, it's going to represent what those values are in Waukegan, not necessarily the entirety of Lake County. So it is important to remember your spatial scale and what you're actually trying to answer. Some systems are more refined than others. You're going to find that out, and probably you already understand that if you have to pull precipitation data. Missing observations are a common problem with station-based observations. So much so that some of my colleagues who are researchers skip over station observations altogether and go to other products. I'll talk about those in a second. They're handled differently by different systems. If there's missing observations, there's not much we can do to fill in those gaps. So that's something that we'll have to do. Now, there's some stations, and you'll find these out, that do a better job of keeping a consistent record. So if you're looking at observations over the last 70, 80 years at O'Hare, there's very few missing observations. But some of the other stations that are not at kind of those large airports may have a few missing observations. And then also importantly, the past is not always predictive of the future. The past climate, as we understand, is not what the future climate necessarily is. So if you're representing trying to quantify risk using past observations, it's a great way to start, but understanding that may not necessarily be the best option available for representing future risk of any kind of hazard. Go to the next slide. Okay, so the next one I want to talk about is gridded observed weather and climate data sets. So the idea again, one of the main limitations of weather station observations is that they're at a point. So it's at O'Hare, it's at Midway, it's at Naperville, wherever. What many centers have done, including at NOAA, is take all those observations and basically smooth them into a grid. So it's a consistent, in some cases, fairly high spatial resolution grid across the country, across the world, across a region. So the benefits of these data sets is that they're spatially and temporally consistent. There is no missing data, except in some cases over Lake Michigan, but at least over land, no missing data. There are many options for temperature and precipitation for these data sets, but there's fewer for other variables. It's very, very challenging to find and use gridded observations of something like wind. But for temperature and precipitation, there are many, many very, very good solutions. Many of these data sets go back to the 1960s or so. Some go back to the 1800s, but oftentimes when you go back that far, you're going to get monthly data, not daily data. The reason being is that if you think just even in Illinois, going back to the late 1800s, there weren't a whole lot of weather stations. So we certainly, basically, if you're trying to turn 10 weather stations in the 1890s into a 1 mile grid across the whole state of Illinois, you're going to be making up a lot of data. So that's why a lot of those daily data sets go back to the 1950s, 1960s. Um, Benefits of these data sets, they're very easy to access and use, especially if you're used to gridded data sets. If you're used to raster data sets, most of these are directly importable into ArcGIS or other GIS platforms, and especially for areas. So I mentioned the limitation of using one point. In this case, it's a lot easier. If you're looking at the entirety of Lake County or Kane County, you can pull these gridded data sets and aggregate them to the county level. In some cases, that's already been done, as I'll mention here in a little bit with the NOAA NCLIME div data set. But municipalities, watersheds, all those sorts of things. I will say that gridded climate data is sort of it's been rapidly the whole kind of climate data infrastructure has been rapidly moving to gridded data for work and assessment, just because it does make it easier to do that kind of long-term assessment, especially over those spatial areas, as opposed to using individual points. Go to the next slide for me. So there's some gridded observation data access points. Google Earth Engine is super powerful, perhaps not as user-friendly as it could be. There's a data set called GridMet that is really easy to port into a GIS framework or a Python notebook. NOAA's NCLIME Grid is actually the data set that goes behind all of NOAA's climate summaries. So anytime you hear me or somebody else say this was the 10th warmest. We actually had the warmest April on record for the state of Illinois last month or 2 months ago. That's based on NOAA NCLIME Grid. And I will say that for those of you working at a county level, NOAA has already taken out the aggregation part of it and aggregated all of the gridded data to county level. So you can get county level precipitation and temperature, just bulk download, nice and easy. And I have the link there. Um, Things to remember. Uh, the way we go from point observations to a grid is an interpolation. Interpolation types vary. Anybody who's got a geography background kind of know that. Some data sets are going to be better than certain applications than others. Really good news. We don't have mountains in Illinois. So that means that it's a little bit easier to interpolate things. But we do have a big lake in the northeast corner of the state, and that can affect temperature precipitation. So again, how you're using that interpolation, it can vary. Something to play with. Finer resolution does not necessarily mean better. Gosh darn, if I could just say, I should just say that at the top of should be my title. If you can get data at the block scale, that's great, but it's really important to remember we're not measuring precipitation at a city block scale. So anything going down to that level is making up data. Now, is that a bad thing? No, if you need that for modeling, that's just what you need. However, we need to be thinking about parsimony and computational resources. And if you want something at a block scale, but you don't need it that much, all you're going to be doing is wasting computation time. So a lot of cases, the NCLIME grid, the Prism, the GridMet data sets that are at between a 1 and 5 kilometer resolution are perfectly fine for most things that you're doing. Also, extremes may be underestimated or smoothed in gridded data. This is the case, right? I mean, we know that with many of the heavy precipitation events, like one we got, I believe it was last year on the west side near the UC, where they caught like 8 inches of precipitation, right? The grid cell that sits over the west side of Chicago is not going to show 8 inches of precipitation because only a very small area of that grid cell got 8 inches. It's going to be smoothed out. So when you're representing things like extremes, we have to keep that in mind when we're using that gridded data. Go to the next slide for me. Here's a QR code to my favorite gridded climate data portal and kind of workshop. It's Climate Engine. It's free to use. You have to have a Google account or I use my U of I account, but it's free to use. And many reasons I like Climate Engine. I went away from a live demonstration because we know those never work. But when you go on there, there are a plethora of data sets you can use. Precipitation, temperature, but also drought data sets, remote sensing data sets if you want to pull in like greenness indices and things like that across your region. And it's really easy to aggregate to different spatial levels. You can do region, you can do state. If you're working with a weird, like if you're, for example, if you have to look at precipitation or NDVI across the Des Plaines River watershed, right? You can actually pull in a shapefile of your study area and it'll aggregate the data to that shapefile. And it takes a couple of minutes to do that. So super, super. I see Leslie mentioned love Climate Engine. I do too. I'm not being paid by the Climate Engine people. This is a complete free user advocate here. So I definitely, especially if you're looking and analyzing climate, drought, weather data across a region, definitely check out Climate Engine. It will likely speed up your processes. Now, if you're somebody who really likes to pull in APIs and do the hard work yourself, Climate Engine's cousin Google Earth Engine is probably the way you want to go. But for those who don't like touching Python or R or don't know what those things are, Climate Engine's your go-to. Go to the next slide. Okie dokie. Let's talk about projections real quick. So all of those things that I just talked about were past data. Now let's talk about future climate data. I borrowed this slide from a colleague, Christy Proistasescu, here in the U of I, because I like the way he kind of thinks about this. Is that future climate projections are not actual observations, right? They're model representations of a world. Is it the real world? No, it's some world. And so we have to remember that. But they can be useful, those model projections, in understanding the possibility, the extent of things like risk. Go to the next slide. So, the way that most of these large coupled climate model simulations are run is under scenarios. And these scenarios are basically differentiated by the amount of what we call radiative forcing or warming. You can see the CMIP 6, the latest Intergovernmental Panel on Climate Change, IPCC's coupled model and comparison project. CMIP 7 is coming out in a few years, but CMIP 6 is here now. The different radiative forcing, meaning how much warming, how much global warming essentially are we going to be seeing? And we can run the different models under these different scenarios because we don't know where we're going to end up by 2050, by 2080, by 2100. And so we can say under these different scenarios, here's what temperature looks like. Here's what precipitation looks like. And you can see the plot on the right. This is from CMIP 5, but very similar. A global mean temperature and how that changes, or how that's different, especially as we get out in late 21st century for the different scenarios. I do not recommend only using one scenario. It's oftentimes important to use more than one to understand the sensitivity of whatever you're trying to get at. So if you want to know what the extreme storms look like or drought risk looks like in a specific area of the Chicagoland region, using more than one scenario can give you that sensitivity. And you could get a very small difference, which is great. That means that your whatever your parameter is not all that sensitive to scenario, or you can get a huge difference, which means that we really need to be quantifying what those differences are in your risk portfolio. Go ahead and go to the next slide. And what's really important here, lots of things are really important. This is one that these models are run globally, but we oftentimes trying to use them for the local response. And the local response of the local climate, like for the Chicagoland area, could be different than the global response, likely will be. So I show that the change in extreme rain that's projected versus the change in drought. Oftentimes we can hear sort of national or global narratives applied to local regions, and that oftentimes doesn't work. So it is really important to be looking at what the local response is and not assuming that what's true for the United States or the Western Hemisphere is true for Chicago. Go to the next slide. Okay, this is I like talking about uncertainty. Uncertainty can be seen as a bad thing, but in reality it just is, and it exists whenever we're trying to predict the future. And so what this is showing is, think about this going out in time from nothing, good Lord, from today out to 100 years from now. What this is showing is the breakdown in the uncertainty of your projection. So if you're trying to know how much rain will my area get, how much drought, what's my risk of drought, here's where that uncertainty comes from. The blue is showing you model uncertainty. That if I use model A or model B, how much difference is there? Is the model getting it right? No, the model's getting it wrong, but how wrong is the model getting it? That's that uncertainty. You can see that that's fairly small as we go out in time. And it grows and grows and grows. And by the time we get out to the year 2080, 2100, it's the largest source of uncertainty, right? And that's just because models, the future is hard to predict. The climate system is complex. Models are going to have different ways of doing that. The green is showing your scenario uncertainty. And this is really important to note that if you're looking at different scenarios, right, the high emission scenario, the low emission scenario, that sort of thing, you're going to see the largest difference as you go out in time. Sometimes I'll have folks who are looking at like climate projections for the next 20 years, and they use like 5 different scenarios. And it's like, well, there's no difference. Well, yeah, there's no difference because there's a very little difference in the actual warming change between those scenarios in the next 20 years. It's really when we get up to 2080, 2100 that we see those differences. The orange is the weather uncertainties, you can call it the weather variability. Notice that that is by far the largest source of uncertainty over the next 10 years. So if you're using climate projections for the next 10 years, you're not really going to see much of a climate change signal in most things, especially with precipitation. Because what happens over the next 10 years is more of a function of weather variability. We have a drought year, we have a really wet year versus the climate change signal. We're going to start to see that uncertainty dissipate as we go out in time. So it's really important to understand that if you're using climate projections to quantify risk, anything before the year 2050 is likely going to be more influenced by year-to-year weather variability. Beyond that, that's where we start to see that climate change signal. Go to the next slide for me. Okay, lots of things, lots of different access points to popular data sets. None of these are user-friendly. Some are better. None of these are user-friendly. We do a very poor job in the climate science of making climate projections useful and usable. Something that we're working on, but is really challenging still. Some of the more popular data sets are NASA's Next GDDP. That's a really good data set. LOCA 2. I'm getting a text that probably means 1 minute. Yep. And Argonne's Climber and World Climb. Go to the next slide because everybody will have these links here. Two of the products that I like that I think are somewhat user friendly are Argonne's Climber, which is, local sourced, right? Just like your meat and vegetables, we can locally source our climate projections from Argonne. And then the government is, or the Fed's climate mapping for adaptation. The reason I like Argonne's Climber is because they include many more data sets or many more variables and allow climate projections to be assessed for smaller areas or aggregated areas. So it's not completely unlike Climate Engine. Um, and so they have a pretty good kind of input for interacting with those climate projections. I think this may be my last slide. Maybe check one more. I can't remember if I have it. Oh, questions. Yes, it is my last slide. So with that, I'll wrap up and I'll say that especially with any climate data, like I mentioned, definitely reach out as you have questions, problems, accessing. Certainly with climate projections, it's not just about getting the data, it's about how best to use the data and asking the right questions. So if you have any concerns about, yeah, I can get the climate projection data, but I don't know how to use it, definitely reach out. We can walk you through that process. So thank you very much again for the CMAP folks for letting me come speak today.
Great. Thank you so much, Trent. So there's a lot of resources to explore there. In the interest of time, I think, Trent, if you could go into the chat and answer questions there directly, because we're running a little bit short on time, that would be great. So thank you so much again. And so our next speaker is Scott Kunkendale. Scott is the Water Resources Specialist for McHenry County, and I'll go ahead and turn it over to you, Scott.
All right. Thank you, Margaret. I'm just putting some links in the chat here. Oop. All right. So am I ready to go, Margaret?
Yeah, you're good.
All right. Thank you.
Thank you.
All right. Hello, everybody. Thank you for the opportunity to speak with you today. So my name is Scott Kuykendall. I'm the Water Resources Specialist for McHenry County. I help oversee our scientific research into water resources, help set public policy to protect water resources, maintain the county's environmental compliance, and then I do a lot of public education and outreach. So what we're going to be talking about today are resources that we have specific to McHenry County, and why these won't necessarily be replicated elsewhere. I think they are powerful tools to help us understand how our water resources work and react to changing climate patterns. And so we're going to be focusing specifically on shallow groundwater resources in McHenry County and in the region. Although we're going to be talking about things specific to McHenry County, a lot of the mechanics are the same. If we're pulling water out faster than it's naturally being recharged, then water tables drop. And that'll be the same no matter where you are in the world. Next slide. So this is a map showing the distribution of water resources in the state. So of course, in the northeast corner of the state, we have a lot of dark blue. That's all Lake Michigan water that's extending from Lake Michigan inland. But most of northern Illinois gets their water from groundwater. So that's shown in brown. And all these resources are public water sources, municipal water sources. But groundwater is the primary source for most of northern Illinois and a big chunk of central Illinois. As we move downstate, the availability of Lake Michigan and groundwater disappears. Most of the light blue that you see downstate are reservoirs that have been constructed by damming up rivers or streams. They don't have the groundwater resources that we have up in the northern part of the state. Reservoirs can be great resources, but they require a lot of land area, very expensive, can have water quality issues, and you're potentially losing a significant amount of your water to evaporation. Next slide. This is a great map that the Illinois State Water Survey put together depicting the geology of Northeast Illinois. So of course you have Lake Michigan on the far top right. The uppermost layer of aquifer is shown in brown. That's layers of sand and gravel that were deposited during the past two glaciation periods. Below the sand and gravel is a layer of limestone or dolomite. So these are our shallow aquifer resources in Northeast Illinois. And the great thing about these is that they're recharged locally. When it rains or snow melts, water is able to percolate down through the pore spaces between the sand and gravel particles and recharge aquifers locally. Water that passes through down to the limestone can fill in cracks and fissures in the limestone. But those are our local shallow groundwater resources that are recharged locally. We also have deep bedrock aquifers shown in blue. The uppermost one's the St. Peter, that's largely been desaturated. The Ironton-Galesville is the main aquifer that we use for our deep water aquifer in the region. And that water is actually recharged largely up in Wisconsin, where the rock layer rises up towards the surface. So that is not recharged locally. And it takes 1,000 years for water to land up in Wisconsin and make its way down here. So that is a non-renewable resource, whereas our shallow aquifers are perfectly renewable as long as we take care of them. Next slide. So this is a map showing the different aquifer types in the state and their distribution. And once again, you can see we have a lot more access to groundwater in the northern part of the state as opposed to the rest of the state to the south. Now, the sand and gravel, you will see a broad area of sand and gravel aquifer in the center part of the state, and that's an important aquifer. It's called the Muhammad Aquifer, and that is the sole source of water for that region. So Champaign has no other water resource availability other than the Muhammad Aquifer. So if something were to happen to the Muhammad, whether it's contaminated or if it's pumped dry, they have no alternate sources. So that is a sole source of water for that region. And so it's really important to understand the opportunities and constraints of your water resources. Next slide. So we're closing in once again on Northeast Illinois. Of course, the light blue is Lake Michigan. That is not an infinite amount of water. We have a fixed amount of water that we're allowed to take out of Lake Michigan. And then you can see McHenry County up in the top left. That's where I work, and we're 100% reliant on groundwater for our drinking water resources. We were experiencing exponential growth in the early 2000s, and our county board wisely asked, do we have enough water to support this growth? And so we actually have done a lot in McHenry County to understand our water that is pretty unique. Next slide. Now, our water resources are vulnerable to a variety of threats. Overconsumption is one of the main ones. If you're pumping water out faster than it's naturally recharged, water tables drop. Our shallow aquifers are also very susceptible to pollution. Any pollutant we put into the air, onto the land, or into the ground can percolate down and contaminate our aquifers. Flooding, sometimes we get too much water, and then drought, sometimes we get too little. And we'll talk a lot about the resources that we have and how we are tracking drought. Next slide. So this is a great animated slide that an engineer named Jane Patchett put together about 40 years ago, and I've spent 40 years trying to find something to replace this, and I haven't found anything better. So it's showing how natural hydrology works. So before we started paving over and compacting the soil, when it rained or snow melt, the vast majority of the water would percolate down through the ground and recharge our groundwater aquifers. But water is not just standing still, it's in constant motion. So it's moving downward and laterally. And so over a period of days, months, years, decades, or more, it's slowly moving through the ground and providing a base flow of cool, clean water to our lakes, rivers, streams, and wetlands. Next slide. Click it again. But as we urbanize our landscape, we compact the soils, pave over them. So instead of water percolating down through the ground and slowly recharging our lakes, rivers, streams, and wetlands, it hits the land surface and rushes off, carrying with it any pollutants it comes in contact with. And instead of a slow recharge to our lakes, rivers, streams, and wetlands, it creates a flood stage followed by drought, flood, drought, flood, drought. So completely altered hydrology. And the more we pave over areas, the less groundwater recharge is occurring. So the irony is where we have the most people and need the most water, we're recharging our aquifers less and less. Next slide. And when we talk about groundwater resources, it's not just a single layer of sand and gravel throughout a region. Some areas will have 100 feet of sand and gravel, some will have nothing but clay. But what you see more often is a layer of sand and gravel, a layer of clay, a layer of sand and gravel, a layer of clay, a layer of sand and gravel, and then your bedrock. Those layers of clay are called confining layers. And so if you have an aquifer underneath 40 feet of clay, one of the benefits of that is that that clay layer can reduce the potential for pollutants to infiltrate down to your aquifer. So it can protect the water quality of that aquifer. The challenge is that the thicker that confining layer, it's also going to be restricting the flow of water. So a confined aquifer can be much more susceptible to drawdown if it has a thick layer of clay or non-permeable material above it. Next slide. So this is a map showing the groundwater wells in McHenry County. So we have records of over 20,000 private wells, and that's a gross underestimate. We probably have about 30 to 40,000 private wells in McHenry County, all relying on the shallow aquifers. Next slide. Now, when we zoom in a little bit, you start to see individual blue dots and just get a sense of how many wells we have in the region. Each of those blue dots is representing an individual well, and then there's a number next to it, and that shows the depth of the well. This is a very important resource for anybody to use. So this is based on the State Water Survey's ill water records. And you can click on any of those blue dots, and when drillers drill their wells, they record the geology that they encounter as they go down. So you can click on one of those blue dots, and it'll pull up the well log showing the geology for that well. And so this is something everybody has access to, and I did put a link to the state website on in the chat. So please check that and bookmark that. This is a resource that you can use to check a lot of the information that we'll cover. Next slide. So we've had several periods of drought in the county. This is using Molly's website here. Go to the next slide. In McHenry County, we had what I refer to as a cloud of drought over the county for about 5 years. I did speak to NOAA folks and asked if there was a reason or a name for this type of drought, and the official name is bad luck. So these types of things happen. Go ahead to the next slide. This is current conditions. Next slide. So this is one of the resources that we have. We have a network of 37 groundwater monitoring wells distributed throughout the county. The U.S. Geological Survey maintains this for us, and they did a great job coming up with a website that's really easy to use, and it's open to the public. It's color coordinated to show both where our wells are and whether water levels are normal, low, or high. So green being normal, various shades of red are dry, various shades of blue are wet. These are taking water level measurements every 15 minutes and transmitting this data to U.S. Geological Survey satellites. Next slide. We also use this well network for water quality monitoring. Every 10 years, we're going to each of our monitoring wells and collecting samples and running a full battery of water quality tests so that we can track water quality changes over time. Next slide. You also can't look at the land surface and understand what's going on underground. So we worked with the Illinois State Geological Survey to do three-dimensional mapping of our subsurface geology. It's my understanding that Lake County and Kane County have done this as well. And Boone County to our west just started the process, and they're using helicopter aerial overflights to do theirs. Go one more slide. You can go anywhere in the county and run a transect line, and it'll pull up the geology underneath that transect line. The dark colors, greens, blues, and dark pinks are areas dominated by clay. Light colors, the yellows, golds, and browns are areas dominated by sand and gravel. So those are our aquifers or the recharge to those aquifers. Next slide. So this is showing changes over time. So 6 months ago, most of our wells were actually low. And within 6 months, we've gotten a lot of rain, and a lot of our aquifers have recovered. And we've been collecting data since 2009. Go to the next slide. And so having collected that data continuously since 2009, we are now getting a much better understanding of how the different aquifers in the county react to changing climate patterns. So we've captured several periods of drought as well as a period of record rainfall. And in 2012, we had a catastrophic drought throughout the Midwest. Water tables dropped. But you can see that was followed by a period of record rainfall, and our aquifers recovered. This shows the resilience of our shallow sand and gravel aquifers. In many parts of the country, if the water table draws down, the land subsides. Ours is much more resilient. Next slide. But different aquifers react very differently. So this is an aquifer that reacts very quickly, rapidly to changing precipitation patterns. If we go to the next monitoring well to the east, you will see a thicker line. So we'll go one more ahead. So this is the next aquifer to the east, and very similar pattern, but the thickness of the lines have changed. And this is because this is right next to several supply wells for the city and 2 golf courses. So every time they're turning their pumps on, that's creating additional activity. And so that is what generates the thickness of that line. Next slide. This is a very different pattern where it's very sharp rise and fall, sharp rise and fall. And this is because it's right by a creek. And so it shows the hydrologic connection between our surface water and our groundwater. Next slide. This is a very different pattern here where we had a drawdown start in 2020, and it really has not recovered. This is because there's 70 feet of clay over that well. We had a resident call us saying that he ran out of water, and it's in the same aquifer as this one. Next slide. So we'll go ahead and go one more slide. So the resident is in a subdivision. He was the 8th house to go in, and he ran out of water in less than a year. He's in the same aquifer as our monitoring well, and that pattern corresponds with his experience. But he's the 8th house in a subdivision slated for 80 houses. What's going to happen to that water table when the other 72 houses are built? We really need to be tracking this type of thing. Next slide. The last scenario here, this is a monitoring well right next to a large subdivision that's slated for 4,500 new homes. So starting in 2020, the development started, and almost immediately we saw a decline in the water table that has persisted year after year for the past 5 years. This is completely unsustainable. And the pattern that we're seeing is probably due to irrigation. So in the spring, the pumps go on and the water table drops. It recovers in the fall when they turn the water level off, but in the spring, the irrigation starts again. So you see a declining pattern. This has prompted the city to proceed very quickly to drilling deep bedrock aquifer wells from a non-renewable source because that's the only way they're going to be providing water. Next slide. This is just another 3-dimensional map, so showing how I'm using both our monitoring wells and our 3D maps to track things going on underground. Next slide. And so I think I'm at time here. I'm happy to answer any questions. Sorry to kind of run through that, but I really think this information helps people understand how our groundwater works. And as you travel around the country, you can use this information to better understand how water works in different regions. And I put several resources in the links, including our website here. which has links to all of our county resources. So any questions?
Great. Thank you. Thank you so much, Scott. That was incredibly insightful. And thanks for sharing how McHenry County has developed and used our groundwater monitoring network to better understand the very local water resources and drought impacts and how that relates to planning. I do have a question for you. So I believe McHenry County is a leader in the state on this kind of monitoring network and how it's available and presented to the public. So if another county or even a community wanted to strengthen its groundwater monitoring efforts, do you have any advice for them based on your experience in McHenry County?
Well, Kane County is in the process of working with the State Water Survey to replicate what we have. So they're focusing on the shallow aquifers. So you could work with the State Water Survey or the U.S. Geological Survey to try and come up with a strategy for installing wells. The technology is being rapidly developed to use different type of technologies that can help bring the costs down. So, like I said, Kane County to our south is trying to replicate the groundwater monitoring well network. There are other monitoring wells, both on a state and a county level. If you work with the State Water Survey, you can manually monitor the wells. So you get a tape and you can go to each well and drop your tape down. It beeps when you get to the water level. And so you can start tracking that over time, but that is pretty intensive labor in that regard. But there are ways to do this on a much less expensive level. And then I did put a link to the U.S. Geological Survey's website where they have all the well data for the country. And so if you do have USGS wells, they may have data, but it's not going to be as widespread as what we have in McHenry County.
Okay, great. Thank you so much. That's all the time we have for questions, but if anyone does have questions for Scott, Scott, are you going to stay on? Maybe people could put those in the chat.
I'll stay on throughout the rest of the day, and then you have all my contact information right there. And like I said, all of our resources are on mchenryh2o.com.
Okay, great. Thank you so much, Scott.
Thank you.
And so before we head into break, we would like to revisit our initial poll questions. Hopefully you do still have your Mentimeter poll open. If not, you can go ahead and scan the QR code or click on the link. And so revisiting our first question. So now after you have heard these presentations, how familiar are you feeling now with drought monitoring tools and resources compared to the beginning of the session? Are you now not at all familiar still, or slightly familiar, moderately familiar, very familiar, or extremely familiar? So please go ahead and select the answer that best reflects your current level of how familiar you're feeling. Okay, so please do keep answering that question, but we'll go ahead and move to our second question as well, which is open-ended. And so now that you have heard these presentations, in what ways do you think climate and drought conditions affect water supply? So again, it could be just a couple words. Maybe you can talk about something that you just learned in the presentations that you didn't know before. And if you are having trouble joining Mentimeter, please do reach out in the chat and we'll try to help you do that if you haven't joined yet. Okay, it's very quiet in Mentimeter. Maybe people are just ready to take a break and stretch their legs. Okay, here we go. Contribute to economic inequities, water shortages, water use conflicts. Okay, so we're seeing some responses come in. We appreciate you sharing your perspectives, and we will keep the Mentimeter open in case you want to add anything. But we are now going to transition to a 5-minute break so we can get a drink of water and stretch our legs before we move into our next session, which we're really excited about, which will introduce some resources that can guide water suppliers through climate action planning and water shortage preparedness. So let's take a break and looking forward to seeing everyone back in 5 minutes, which will be 10:30. So welcome back, everybody. I hope you had a good break. Our next session is climate and water utility planning. And we will be introducing some resources that can guide water suppliers through climate action planning and water shortage preparedness. And so we do have two speakers in this session, and we'll be hearing about the American Waterworks Association M71 manual, as well as the M60 manual. Before we dive into our first presentation, we do want to get a sense of where everybody is in the room in terms of how familiar are you with the American Waterworks Association M71 manual. Hopefully you still have your Mentimeter poll open. Again, if you don't, you can scan the QR code. So we're really curious to know if this is your first time hearing about the manual, if you've already used it in your work. And your responses to this question are really going to help us understand the range of experience that's being represented here today. So have you never heard of the manual before? Have you heard of it but never used it? Have you actually reviewed parts of it? Or have you used it in your utility planning or operations? Okay, so it looks like so far most respondents have never heard of it or heard of it but never used it. So you are in the right place to hear more about it because our next presentation will be giving us a shared starting point in terms of what the AWWA and M71 manual is and how it can support climate planning. So with that, we will move on to our first speaker in this session, who is Rachel Duncan. Rachel Duncan is with Carollo Engineers. She is the Resilience Management and Water Supply Planning Lead. She helps utilities build resilient infrastructure in a changing climate. She specializes in climate vulnerability assessments and strategic supply planning using sophisticated modeling and rigorous alternatives analysis to guide decision making. Rachel currently chairs the AWWA Climate Change Committee and co-chairs the update to the AWWA M71 Climate Action Planning Manual. She holds degrees from the University of Illinois and Stanford University. So please join me in welcoming Rachel Duncan.
Thanks, Margaret, and good morning, everyone. Let's go ahead and dive in. I was glad to have that poll before this to understand where folks' familiarity is with the AWWA M71 manual. Sounds like there's some folks who have heard of it. No one's used it yet, so that's exciting for me to get to introduce this resource to you, which hopefully you'll find useful in your climate action planning efforts. So if we go to the first slide, and the poll question that we had before the break teed us up really nicely for this discussion, kind of providing an overview of what different climate threats to water supply in the Midwest are, which of course a lot of the previous speakers in this session have touched on in various ways as well. But essentially we're looking at impacts to water quality as we see temperatures increase in the future and greater instances of extreme precipitation, which can lead to increased pollutants in watershed for surface water supplies, as well as toxic algal blooms and invasive species. On the water quantity or availability side, we've got combinations of extreme heat and extreme drought, which we're hearing about from NIDIS and from others, which leads to just overall decreases in water availability and increases in water demand. So you've got greater potential gaps. And then on the vulnerable infrastructure side, we're seeing the combination of aging infrastructure with extreme events and extreme storms impacting the ability to reliably operate systems. So with one more click, we see that the question that all these potential issues raise is how do we engineer for reliability when historical weather and climate data is no longer a safe predictor of the future. So if we look at trying to engineer for what we call the cone of uncertainty, where we're looking at uncertain futures, depending on what is in store for us in terms of our future climate. And so here we've got a little contrast between what we think of as traditional engineering, how we've been planning our water systems and water supplies and designing our systems to deliver those to customers for the past, 100+ years, to shifting towards a mindset of adaptive management, which is really the focus of the M71 manual. So within traditional engineering, we're typically assuming what we know of as stationarity, which is that weather patterns will continue in the same way that they have historically, whereas under an adaptive management mindset, we're thinking more about shifting towards non-stationarity, where we've got shifting distributions and what rainfall patterns will look like, what temperature patterns will look like. I'm located out here in California, and we're looking at how changes in seasonal precipitation and seasonal temperatures affect snowpack, which is a major source of our water supply. So thinking about the possibility for different differences in the future that will look different than what we've seen in the past. In terms of looking at the future under a traditional engineering mindset, we would plan for what we call an M71, a cylinder of uncertainty, or a more single predictable outcome, whereas shifting towards adaptive management is where we get into this cone of uncertainty and considering multiple future scenarios and deciding, as was mentioned earlier by the great presentation from the state climatologist about considering multiple future scenarios to think about what the sensitivity to those future scenarios is of our current system so we can understand what to plan for. In terms of design approach, typically we've understood that we need to build our systems to meet some sort of maximum capacity. There's a static safety factor that we build into our calculations. But when we're thinking about climate adaptation and designing those into our systems, we want to try to build more flexible systems with potential incremental changes for future redundancy as climate conditions change. And then finally, when we're thinking about things on a risk management perspective, particularly with responding to extreme events, we have typically relied on emergency response plans and procedures to respond to unforeseen events, which are those are great tools. We're not saying any of those are something that we should go away from. We want to make sure we have really good, robust emergency planning. But under an adaptive management mindset, we want to start thinking about integrating probabilistic risk directly into our capital planning to, again, think about those potential multiple futures and the sensitivity of our system to those different scenarios. So if we go to the next slide, this is where the purpose of the M71 manual is to provide clear guidance to water utilities of all sizes to proactively assess climate risk, design resilient responses, and optimize resource spending to meet these goals. So this is intended to be a clear and structured roadmap designed specifically, very geared, as AWWA is, towards water utilities to help them in planning, executing, and evaluating climate adaptation strategies. So I'm not going to spend too much time going over the structure and content of the manual and focus more on the practical application, but there are sections about integrating climate science with core engineering principles, thinking about how to translate these high-level projections that we're hearing about in terms of what we can get from downscaled global climate models and other sources into how to integrate that into your actual capital improvement plans, and then how to continue to monitor situations, monitor the performance of your system, and adapt as things change. So one more click, we can see that structure of the contents. As I mentioned, there's some upfront material relating to the science of climate change, principle of engineering science, some introductory things about what a climate action plan is and is not, and why utilities need one. The real meat of the manual comes in the second half, which is in how utilities develop a climate action plan or CAP and keep it current. I will note that there are sort of two different potential focuses for climate action planning manuals. There can be or not manuals, but climate action plans, there can be more of a focus on climate change adaptation. So where you're looking at how to build more resilient systems to with respond and withstand to climate threats. And then there's also climate change mitigation, where you're looking at reducing your greenhouse gas emissions to lessen the overall, your utilities' impact on climate change. Given that that's not the focus of today's session, I don't spend much time talking about the mitigation component of what's included in M71, but did want to mention that it's in there for anyone who's interested. And then we also have pretty robust information regarding how to get stakeholders involved in the climate action planning process, and to really kind of juice that public participation to get buy-in. And we also have information about estimating the cost of a climate action plan, as well as some financing structures that you can use for the planning process itself, as well as for financing recommended projects and adaptation strategies that come out of the climate action plan. And then finally, we end up with some case studies of existing climate action plans that have been implemented from water utilities around the country and specific adaptation measures included in those plans. I'll mention that this manual came out in 2021, and we have just started as of this year embarking on an update. So it'll be the second edition of that manual. That process takes a couple of years, so it probably won't be out until, let's see, 2028 or so. But in that expansion or updated version of the manual, one of the areas that we are definitely focusing on building out is making sure that those climate action plan examples are more actionable, more useful for utilities, and more up to date, since a lot more climate action plans have been developed over the last 10 years or so than were available when this manual was first published. All right, let's go ahead and talk about what a climate action plan is and what it isn't. So a CAP is a long-term dynamic guide built to manage climate risks. They should include, if it's more mitigation focused, and I will say some climate action plans include both a mitigation and an adaptation focus. Some are more in one than the other, but if you have a mitigation focus, should include that framework to actively track and reduce greenhouse gas emissions. If you've got more of an adaptation frame or focus, then you'll be looking at measures to prepare your critical facilities for climate impacts such as severe droughts and floods. And then should include operational guidance to help meet either evolving climate conditions, regulatory standards, policies, etc. A climate action plan is not a replacement for existing emergency energy or investment plans, although it may include components of all those plans. Your utility still needs an emergency response plan that goes into the detail of, short-term responses to disaster situations. It's not only an energy audit. If you've got more of that climate mitigation focus, that will be a component of it, but an energy audit is typically a little bit more simple, and a climate action plan is saying, okay, what do you do about it? And it's also not a standard CIP list, because we're looking to do a risk-informed list of or planning for potential projects, not just a checklist of sort of standard upgrades and routine maintenance. So looking at what the components of a robust CAP are, so typically you'll be looking at hardening assets. So I will say, the focus of our discussion today is primarily looking at climate impacts to water supply. M71 does definitely include this and touch on this, and a lot of the principles included and steps that we'll be talking about can be applied to looking at water supply, but a lot of it is sort of based on looking at more physical, acute impacts to physical infrastructure. So impact of flooding on, pipelines and pump stations, impact of extreme heat on your operations and, operations staff, things like that. So there's this kind of understanding of building resilience through physical modifications to build resilience against natural hazards. Should also include updates to your utility operations to adjust day-to-day procedures to maximize your flexibility. So for example, shifting your pumping regimens during prolonged regional heat waves and responding to both the conditions for your operating staff and also for the needs that your customers have. And then on the mitigation side, looking at carbon control, so tracking, projecting, and mitigating your greenhouse gas footprint. So integrating these components overall in your overall planning process reduces your utility vulnerability and then avoids costly fragmented responses that are more reactive to climate threats than being proactive in planning for the future. So some key logistics in terms of embarking on your climate action planning journey is starting with, I'm actually going to start with the middle section here about making sure that everyone in your team that is working on your climate action plan, whether that's directly or tangentially, has a basic understanding and fundamental knowledge of climate science 101. We often recommend that you start your planning process by bringing in an expert like one of the folks that we've had talking to in the presentation or in the seminar today to talk to your group about climate impacts for your region, what climate data resources are available, appropriate use of that. This is a great time to partner with your local and state universities and scientific knowledge bases to bring that information in so that you can be using common terminology and understand the sort of foundational science to be able to better inform what your risk tolerance are and what your metrics are surrounding what you're going to be planning around for climate adaptation. You definitely want to establish a dedicated planning team with strong pathways to upper management and understanding of decision making so that you are going into this with the support of your board, of your managing directors, whoever that might be for your utility. And then we do want to make sure that you're including a communications plan in your overall climate action planning process to build proactive engagement with the public to address political, regulatory, and any community concerns throughout your climate action planning process. Go ahead. So finally, we'll end up before we get into our step-by-step process here on the business case for creating a CAP. So this is something that varies a little bit depending on the state that you're in, what local and state funding resources are available, as well as what's available at a federal level. As we know, that can change from administration to administration. But having a climate action plan can help unlock funding for competitive federal and state grant application, can help protect your bond ratings as credit agencies are starting to look to utilities to make sure that you've analyzed long-term climate vulnerabilities and have a funded strategy of how to address them. And then it can also be a really good driver for collaboration with your neighboring utilities. So maybe look for opportunities to share expenses in terms of doing your climate action planning and look for opportunities to help each other out with any mutual aid agreements or potential water supply connectivity to help bolster that resilience. So one stat that comes out of some findings in M71, particularly through studies on the East Coast, but has been kind of supported by utilities nationwide, is a general finding that every $1 invested in proactive infrastructure hardening saves $4 to $6 in emergency post-disaster repairs. So there's definitely a sort of dollars and cents reason to pursue climate action plans in addition to making sure you're maintaining your level of service for your customers. So let's get into step-by-step process for developing an adaptation plan. So this process in M71 manual is divided into 7 steps that we'll see on the next slide. So you start with the first step, which is characterizing your hazards. And this is looking at mapping historical events and projected climate pathways onto your system. So we've heard a lot about that already this morning in terms of great sources, data sources that are available to you both locally and nationally. Steps 2 and 3 look at characterizing your system's assets and understanding their vulnerability to those projected climate threats. Steps 4 and 5 involve identifying and prioritizing adaptation measures and understanding what some of those co-benefits are, evaluating them, typically using multi-criteria metrics. And then finally, steps 6 and 7 include implementing your plan and taking action to get those recommendations implemented. So the process that's outlined in M71 has drawn from a bunch of different national resources, some of which we've heard from today, including the U.S. Climate Resilience Toolkit, resources from NOAA, NIDIS, FEMA, others, processes included in the America's Water Infrastructure Act to make this as sort of a standardized and robust process as possible. So we're going to dive into each of these steps in a little bit more detail. I'm not going to spend too much time on step one because we've heard a lot about the local resources available already, but in addition to some of the ones that we've already heard about, when you're looking at acute events, the NOAA Storm Database is another really good way of understanding the frequency and magnitude of historical events in your area. You, of course, want to rely on your very local data, so sort of your operational logs for your system, looking at previous power failures, previous flooding events, any sort of issues that you've had in the past. And then we've heard a whole lot about all the wonderful federal inventories about drought and other climate information that you can use to catalog those historical hazard footprints. If we do one more click, we'll see, again, just a quick note, I think I've made this point already, but that you always want to start with reviewing past information to understand what has occurred. But since we can't rely on historical stationarity as a reliable predictor for the future, we must pair that history with projected future pathways. So if we go to that part of step one, again, we've heard about a lot of great tools, really appreciated Trent's presentation where there was a lot of great, here's a great climate database for this use, here's another one. Some of the ones that I really like are NOAA's Climate Data Online tool and USGS's National Climate Change Viewer, in addition to some of those other ones that were already offered this morning. A lot of context can be understood in more of a sort of written format in our national climate assessments. And then, as I mentioned before, make sure to rely on the regional expertise that you have in the state to understand how this data applies to Illinois, how it applies to your community, how it applies to your region. So we have heard a fair amount about GCM and scenario uncertainty this morning. So I'm not going to, again, spend too much time on it, but we'll understand that there are a variety of potential futures in terms of emissions pathways and what that looks like for our future climate. So it's always good, as Trent mentioned, to select a couple of scenarios to plan around to understand that sensitivity. So moving into step two, this is where you're going to focus on categorizing your assets. So looking at understanding the vulnerability of your assets is kind of a combination of understanding exposure, so how exposed your various assets are to your various climate threats. This is probably most easily understood through the example of flooding, so looking at which of your physical pieces of infrastructure are within your boundaries, projected boundaries of either current or projected floodplains. You want to understand your sensitivity, which is the degree to which an asset is disrupted during a hazard. And then the adaptive capacity, which is the ability to cope or bypass during an upgrade or during a crisis. I know I'm taking a little bit too much time. I'm getting some notes that I have just a couple more minutes. So we're going to go ahead and just kind of lightly touch on the rest of the steps, and happy to talk more in Q&A about what that looks like. So this is just some more discussion around how you can integrate understanding of your system's asset and in this case, water supply vulnerabilities to help you prioritize risks. So if you have multiple different water supplies, understanding which of those are most vulnerable to different types of climate threats, and then prioritizing them to help you prioritize your adaptation strategies, which when we go to step 4 is helping you identify and prioritize those adaptation strategies. So you really want to look at project-specific modifications as well as potential policy shifts, potentially combine those various adaptation strategies into portfolios. It's particularly relevant for water supply options, and then evaluate those portfolios under historical conditions, but also look at both moderate and more extreme future climate scenarios to see how the proposed portfolio of adaptation measures may perform under those future scenarios. Step 5 is more about prioritizing adaptation strategies. And if you do one more click, just want to make sure that we're including not only economic criteria, so thinking about costs and related benefits, but also social criteria and environmental criteria when we're evaluating these adaptation strategies. And then if we go to step 6 and step 7, that's where we're talking about developing an implementation plan, and there's more information in, the M71 manual about what that implementation might look like, and the importance of monitoring, again, your actual climate conditions as well as your system and its responses as you go into the future, and continually updating your plan as conditions on the ground change, as well as we get more refined climate projections for the future. So there's a quick note in here about communicating risk to the public. There's a whole chapter in M71 about stakeholder engagement. So essentially looking at how you can shift engagement efforts from reactively explaining rate hikes to your customers to proactively collaborating on planned investments and understanding which of these levels of public impact and is important for your utility in terms of which stakeholders you engage with and how. And then I have a case study at the end, which, since I know I'm pretty much out of time, we'll go ahead and save for Q&A, but can suffice to say that there is a variety of ways that climate data can be translated into modeling that can be applied specifically to, in this case, this is looking at the whole state of Oklahoma and 82 different basins across the state, but you can also look at it at a much more granular scale for your specific utility. And go ahead and click through this since I know we're at time here. So we'll end with just saying thank you very much for your time. Looking forward to more discussion in Q&A.
Great. Thank you so much, Rachel. As you all can see, the M71 manual contains a lot of really helpful information. And Rachel, you did a fantastic job covering all that in a very short period of time. So thank you so much. We will be holding questions for Rachel until the end of the session, where we'll have a panel Q&A with Rachel and Lisa, but I see some questions are already in there, but we'll be addressing those at the end of the session. So as we transition into our next speaker, we would like to check in. Let's see. Oh, okay. Thank you. As we transition to our next speaker, we do want to really quickly check in. So Rachel just talked about the M71 manual. Lisa is going to be talking about the M60 manual. We are curious to know how familiar you are with the M60 manual. So please do take a moment to scan the QR code, or if you still have Mentimeter up, to quickly answer. And so the options are, have you never heard of the M60 AWWA manual before today? Have you heard of it but never used it? Have you reviewed parts of it? Or have you actually used it already in your planning or operations? And so we are getting some responses in. It looks like, again, pretty low level of people being familiar with that. So thank you for taking the time to respond to that. That's really helpful for us and for Lisa to know as we move into our next presentation. And so our next speaker is Lisa Madhouse. She is co-owner of Madhouse Water Management, which is a 10-person team of water resource, demand conservation, and drought planning specialists. She's a registered engineer with 30 years of experience preparing water resources planning, conservation, drought, climate change, and water loss control studies. Lisa has presented more than 150 times, including for the AWWA National and International Water Association and United Nations. She's also published extensively and been a key author in AWWA Manual M52, Water Conservation, programs, M50, Water Resources Planning, as well as M60, which we're about to hear about, Drought Preparedness and Response, and M36, Water Audits. So please, and also Lisa's team works regular teams with Rachel's team. So please do join me in welcoming Lisa.
Thank you. Good morning. I appreciate this opportunity to introduce you, it sounds like many of you, to the M60, and I was excited to see someone's already applied it. So I'm going to go through, go ahead and change the slide for an overview of the M60. So we're actually in our second version. It was published in 2019. These are provide a lot of case studies. And the next slide. It's a collaborative effort. If you're not familiar with the AWWA manuals, they are manuals of practice that are peer reviewed. They're voluntarily developed. This is our team last time with the version 2 that's a second edition that's out now that I helped participate in. They are a labor of love, and then they are unanimously approved by AWWA, the Technical Education Council. So next slide. This manual breaks down preparing a demand and responding to drought, and there's 7 steps. I'm going to touch on each one throughout this presentation. So you're gonna see the highlights and hopefully get the core ideas. And then I also have a handout. I offered a number of links to other free resources, including some from AWWA I'll be touching on throughout the presentation. Next slide. So step 1 is have your shortage response team. So droughts are, slow kind of burning emergencies, we call them, or can develop into, more dire crisis. So the first part is having a shortage response team. It touches on so many aspects of your utility and team internally. So you're going to need your communications team. You're going to need your finance team. There's going to be budget impacts. You're going to need operations, right? You're going to need consumption data. So you're going to need to assign point people. And there's a good examples within the manual on this. Not only within your agency do you need to know roles and responsibilities, but also neighboring agencies. You may be having a contract or an intertie, and you need to activate that. Who's your point person on the other side? Who are your collaborators? Are there local tribes? And then we talk about regionally a news shed with drought. So sometimes your utility may have one risk profile and supply portfolio and not be as direly impacted by this drought. For example, you rely more on groundwater and less on surface water, and it's more of a surface water impacted drought. Then you may be having different messaging that you need. So understanding what's happening regionally and how a news shed of the drought and the water shortage in the regions affecting you is really important. Along with the community is a huge partner, and how to utilize non-governmental agencies to participate in drought response, but also you're asking for all the water users to respond and reduce their demands. Next slide. So part of that is setting different priorities. There's a number of examples, but we really try and minimize financial impacts. There definitely can be economic hardship. It can affect individuals and small groups, and equity is an important consideration. And we're trying to restrict overall less essential uses before essential uses. So that means fire protection is first priority. Second is domestic health and sanitation. Water, your indoor water uses principally, and keeping businesses functioning. Businesses I'm in California, our water code here delineates that, those fire protection, domestic and sanitation, public health and safety uses first. And then after that is business and agriculture, and others are interruptible supplies. So just kind of keeping a whole balance and perspective of priorities. Next slide. Maintaining momentum. Having a leader on your team is extremely important. Being prepared, starting in the winter, and having a campaign ready, kind of on the shelf, regardless of precipitation, and that you can plug in information and roll is super important. Hard to have spot contracts or agreements put into place in the moment, needing to have those prepared in advance. And just being ready for new staff and equipment that's ready or on call, or you have vendors that are on call. And some are, here we have actually drive up water stations that are key card coded, for example, in drought response. If you have people show up that have individual wells and are now coming to the utility looking for supply, how would you supply them in an emergency situation? Next slide. Step 2 is being prepared and forecasting supply in relation to demand. So this is when we get into kind of a data analysis step. You need to have, and we just saw some great examples of monitoring networks and understanding where can you get supply data and reviewing all your agreements and having a good solid profile of what is your supply portfolio under different conditions. And then also in the demand space, we need to see monthly data. You want to see what is your available supply by different months, and then also what's expected for monthly demand. And look at it by customer class for the last 5 years, and just understanding it also if there's changes in population or things that have influenced in the past 5 years, or there's a special event or something coming near term that you might see a spike in demands in the coming year or months as you go through the drought, are also really important to document. Next slide. So some of the analyses you'll be looking for is projection for each of your different types of supply, considering different scenarios, like with augmentation, worst case, what is your worst case scenario? And if there was uncertainty and variability, I think Rachel did a really nice job describing and profiling that, how you might frame that up, but there's a lot of discussion, and we actually do modeling of simulating what is a worst case scenario by stacking different variables together. And one of the variables that's always critical is water quality, and how your water supply profile or treatment and budget might increase because of different treatment that's needed as water quality can degrade. Next slide. Well, actually, back one slide. The demand one is also trying to speed up. But the drier demand without and with reductions in place is important to profile and think through your customer classes and who might be able to save how much and in which months. For example, your irrigation, and if you have the peak sprinkling months, if you're able to shave irrigation, how much might that save? And so next slide. And then so be prepared to know how much water you expect to have under different weather and climate forecasts, and your carry out analyses of your past data to answer the questions of what would supply look like. Is there other infrastructure you need to bring online? Maybe it's wells you need to rehab. We just heard about the ability to drill deeper wells or have wells that are maybe on standby that you bring on that are lesser quality, and then you're planning to blend them and how. And then the ability to meet demands with and without supplemental supply. So just looking at careful scenarios, and then also taking a look at disasters. Next slide. There is an important step to look at catastrophic supply interruptions. I live in California. We have earthquakes, except for I live in Sacramento, so I'm not as impacted by earthquakes than where I grew up on the coast of California. But for flood impacts, water contamination, system failures, just how you're going to collaborate with emergency response plans. So those have a lot of operational and episodic, event that happens. But a lot of times drought plans get tapped because they have a lot more detail on demand reduction and immediate demand reduction. If you have to drop into deep stages and get 30, 40, 50% curtailment of demand and in a short order, and there's very clear descriptive drought demand response measures, then that's a lot of times the drought plans are leaned on for that. Next slide. So the balancing the supply and demand, that's where we take a look in step 3 and just make sure that we have some clarity and quantification of what augmented supplies are really available. And if you need to expand your portfolio to new sources or seek opportunities to collaborate with other agencies, balanced by reducing demand, which, when you enact restrictions and things, can definitely create some economic impacts to the community. If you're going to have a drought, modify drought pricing, having the drought surcharges already in place, and then considering and having a rationing and allocation plan already set up. It's really important. Next slide. As part of the deeper, usually we see stage 3, 4, or any of the mandatory stages, that there is enforcement requirements in place, that you have those policies so that a court enforcement team could go out as needed. And first pass through is educational talking to the customer, having clarity on what the rules really are, and usually then in the second, there might be a fine or something just to reinforce that the rules and regulations are necessary. And also it's necessary for the community to understand that there isn't some enforcement happening, so that their behaviors also, are, if their neighbors gutter flooding and no one ever comes, they're not really going to trust or think that their savings matter too, right? So it is a community-wide effort. Some areas like Santa Cruz had a water school, which was like get your traffic ticket and get out of it free. You could get one waived in a 12-month period if you came and listened to why they needed the drought. So, so the deeper level is fines, and then at the extreme level, if people really are not being collaborative at all, then the offenders could go as far as having flow restrictors put in place, and that's like extremely rare that we hear that. It's the 0.01% of customers or less. Like East Bay Med Utility District has over 1 million people served, and they've done a handful of connections. Have they ever had to get to that level? We have snowpack and more surface water droughts out here in California too. So more deeper, extreme, faster, need more enforcement. So it kind of has to align with your local story, how that prevalence may happen. But next slide. This is an example from San Antonio, Texas. Just under tracking what ordinance and violations are happening by month is important. These are call outs, like in the case of, in their case, 1,100 of the 1,600 in total, they didn't find the gutter flooding in the moment or information. Cities use 311 systems, others, and just being prepared that the summer months can peak, so you might need seasonal help or things to kind of respond. My local city of Sacramento, did a ride along with media, just explaining what they do and showing that they're there to educate first, and that actually got a nice uptick in terms of compliance and a downturn in terms of calls. Next slide. Step 4 is establishing triggering levels. So that's understanding how you move from one stage to the next. Those are determined by source. So is there a water quality change? Is there groundwater level changes? We saw a really great presentation on the groundwater levels and triggers, and just understanding what groundwater elevations and your drawdown and what capacity is really going to trigger a needing and demand response is the most important thing to understand. So I have a few examples I'm going to show you. Next slide. So in this case, it's showing a surface water reservoir, and as the drawdown happens, that you need by various stages, what's the water reduction goal that you need to meet on the demand side. So every agency will have its unique mix of sources and then have its water reduction goal assigned to that. And so in the manual, it goes through a good narrative and examples of how to do this and set this up for yourself. Next slide. Here's an example of one for a river-based. The blue line is showing in storage kind of the capacity as it's being drawn down, and you can see they're in the normal level of trigger. So this is in normal conditions, the black line there. So they're tracking normal, no drought triggered, right? But they've quantified for themselves in the yellow what a watch level would be, what the warning and the drought, and it varies by month, right? What they fill and then they draw right off in the fall months and into the river, and then they're refilling again. And so this is how, when you set it up for monitoring, that you are moving through the drought stages. And you can also notice those are stacked pretty close on the front end, that in the spring months, you can move through drought stages pretty quickly. So being on top of the monitoring, the communications, and the demand response tracking is really important. Next slide. This is another example where you have multiple sources coming together and drought indicators. So in this case, there's storage reservoir levels is one indicator. The second is the snowpack level. It's above average or below average snowpack for this utility. What's the river forecast? It's favorable, not favorable. What's the irrigation demand? Is it a dry year and the irrigation's already spiking? Then that will, you can flow through your chart and see what level of drought stage you should be at. So there's other examples of multiple decision trees, but it would be unique to each agency to know how to trigger which stage. Next slide. So the triggering mechanisms, there can be delays or pressure, right? It's community impact. So the longer you delay, the more you can worsen the situation. It could be you're not ready, you don't have well-defined triggers. And really, it's important to, we call it hedging, like be ready a little, like a month ahead. Know that you need to include flexibility and stage things. So I just showed you how short the time window could be, like a month you could move through 2 stages. So be prepared. And the sooner you act, then the lesser the hardship, right? We hope. So next slide. So step 5 is developing a stage reduction program and establishing the stages. There's usually minimum, moderate, severe, and critical. Those are often common. In California, we are actually mandated by law to do a 50+% stage. So we have 6 levels of shortage, but I'd recommend you check with your state or regional or collaborating with a wholesaler if you get regional supply set up for your demand. Next slide. There's a number of criteria for demand reduction actions. They include what's the timing? Can it reduce the results in time? It's fast acting like leak repair and demand. What's the cost to do that on your utility leaks? Season, is it an irrigation demand? You're trying to shave the peak in the summer months. And then what magnitude of savings would you be expecting? Are all necessary. Next slide. So you can evaluate these demand reduction measures, have a method for them, understand like uptake and restrictions, and just prioritizing the measures. Usually we stack them by the most water savings. We consider costs, and if there's any legal or procedural requirements for implementation, the burden on that. So just consider how you stack your demand reduction measures. Next slide. So some quick examples, and there's many in the guidebook, are stage 1 is usually voluntary. You're asking for public information, give people like a quantified savings, like 20 gallons per day reduction, talk to them about behavioral change. Stage 2 is when we move into restrictions and with things with levels of enforcement. We definitely intensify the outreach campaigns. We're usually restricting water, asking people to trim a watering day or watering times, and water upon request. We make it much more visible, and increased rates may be triggered. Although I usually trigger that, I usually like to say stage 2A and 2B, and I do the drought surcharge, recommend that as a second step. That usually gets the boards and others to act sooner and quicker to move into a stage 2. Next slide. Stage 3 is when it's getting really serious and you're looking for like a 30% reduction. Then you're really talking about limiting irrigation by days or times. You may be establishing allocations to larger users, really providing on-site support and reaching out to customers, business training, and others. This is much more involved and hands-on. And then stage 4 is when you really have to get to the mandatory level, including fines and others. Next slide. So I already talked about things to think about, but it's being prepared to do savings, tracking your stages, messaging, and being aware of the lag. It usually takes at least a month for most, or even 2 months for most demand responses to show up in a meaningful way. And being prepared for budget and needing to leapfrog a stage if it's not, the community isn't responding fast enough. And the more visual you make it, the quicker they are to respond, and also remind them to tell them you're doing a good job when their demand reduction goals are being met. Next slide. So in steps 6 and 7, you need to have an adopted plan in place. It's really hard to approve drought policies in the midst of a drought. And then when it comes time, then it's much more easier to, implement the plan in terms of bringing staff on board, having the budget available. I have a really good article on the saving for the not so rainy day, customer assistance, dealing with the media. One of the AWWA Technical and Education Council's reports I have in the handout is about drought communications and using your earned, your owned, and shared. But you have a lot of media opportunity to share your water story in a very meaningful way and get response. So and kind of that use that crisis opportunity. So and then I've talked a lot about monitoring actual use. If you have an AMI system, that's just getting easier and easier. Next slide. That's it. Look forward to answering questions. Thank you.
Thank you so much, Lisa. We really appreciate you sharing that drought preparedness framework and the M60 manual. There's obviously a lot of great information in there. We do have a few minutes for a panel question session with Lisa and Rachel. I see that the chat has been really, really active. I think some of those questions have been answered in the chat, but I do see a few themes emerging that I'd like to ask both of you about. So one theme I see in there, I think the original question was, are caps mandatory? But I think that may speak to a larger issue of like what kinds of plans, and I know we're coming from different states, but the issue is like what kind of plans are mandatory, what kind of planning are utilities already doing, and how can utilities really incorporate climate and drought considerations into planning processes they may already be doing, such as capital improvement planning, emergency planning, long-term water supply planning, etc. And this is a really big question, but the other thing I see popping up in the chat is that better done by incorporating it into existing planning, or should we be thinking about that as a standalone planning process? I think that question is for both of you, but
I can start since I already started formulating some thoughts in the chat, but it depends. The sort of requirements for these vary a lot depending on what state you're in. So I work with folks across the country, and some states are much more you could say proactive, or you could also say prescriptive, however you want to think about it, in terms of requiring water utilities to do these. I unfortunately don't know the specifics about Illinois. It doesn't sound like from, the discussion that is a broad requirement. So usually, I mean, typically these are not driven by regulatory requirements. They're typically either reactive to a major event. So New York did their huge climate adaptation planning as a city for their wastewater utility, for their water utility, after Hurricane Sandy. And that kicked off kind of a truly multi-decade process of climate action planning and updates. So sometimes it's spurred by a acute event like that in the sort of arid American West. We're in the I was going to say tail end, but we don't really know. We're in the middle potentially of a multi-decade drought that is, making a lot of folks realize that they have to change how they're planning for things and do more focused climate planning for their utilities. Whether it's something that's better as a standalone effort or as an add-on really depends on what your utility is already doing. So if you're already doing long-term water supply, like a focused long-term water supply planning effort, that's a great opportunity to add in climate change considerations and layer those on top of your existing planning effort. There's no reason to have it be completely separate. It's generally better if it's integrated with your ongoing processes so that it's more likely to get implemented and adapted. If your utility wants to do a really focused climate action plan that I typically see them be more standalone when they incorporate those mitigation components. Typically that's a little bit less easy to integrate, whereas the adaptation side of things, maybe more easily weaves in with your CIP planning process or your water supply planning process. So that answer is both are great, and it just depends on what your utility is already doing.
Okay, great. Thank you. Lisa, did you have anything you'd like to add?
Sure, I can just say that drought planning, I think you can roll it in when you do your worst case scenario planning. I mean, you need to look at your baseline, and then, drought would be like a worst case, like low scenario, and then demand response. So I think it can be rolled in. In California, they actually require two separately adopted plans. So, different states require different things. In Georgia, where I've done drought planning, it's a very prescriptive top down from the state. Like, they describe exactly like what the drought plans and levels are, and they trigger them, and you're to implement. So, it really depends on where you are and how it's structured. But most do, at least a standalone section or a full standalone adopted plan. And that's the M60s written around like having your own like standalone plan. That's kind of how we view it and kind of does practice. So you're picking that plan up when it's time. But I definitely recommend that you're incorporating it in terms of all your capital planning and infrastructure and other planning exercises, along with and complementary with the M71, that you're looking at your demand forecast with climate change in it, where you're doing this, when you're looking at dry year effects, when you're looking at demand responses. I mean, demand will go up faster. Like in 2012, we had a really dry year. In 2013, and then 2014 and 15 hit us, and we had no snow. We had our governor standing on it like zero snowpack, which is 30 to 40% of our supply in California. It was shocking, right? To us, we'd never seen that. So it just depends where you are, what the responses are, and but I do think careful time and laying out those demand actions against the supply scenarios is super important. And there could be a couple different types of droughts that you could have if you have a mix of supplies. You'd be looking at different impacts. Actually, your worst case could change a little. So
Okay, thank
take
you.
a look at that.
Okay, thanks. We are close to time, but I really do want to touch on a theme that I think is important to a lot of people on this call. It kind of goes back to community capacity and equity issues. And Leslie just dropped a comment in the chat. I would love to do this for all utilities as a consultant, but if it's not required, it's really hard to get clients to agree to the added cost. And then Rachel, I did see you dropped some of the estimated costs for doing a cap into the chat. And so I think it's worth taking a minute to sort of think about how do you think utilities can incorporate all this into planning processes, given that given that both of these manuals seem very comprehensive. So if a community does have limited capacity, what are one or two practical first steps they could take to begin improving climate or drought preparedness if they don't have like that full, I think I saw $200,000 for a cap as a cost, but if they don't have all of that capacity to do all of the steps.
There are certainly a lot of great sort of tools and resources, which, is the whole focus of this seminar today, available to, at the very least, go to the NIDIS drought tools, go to some of those NOAA and other federal tools to look at a general, understanding of generally many regions of the US are getting hotter, right? That's kind of a consistent trend. Precipitation's way more all over the place, so that can be harder to parse, but you can do some pretty basic statistical analysis of some of those projections to get an understanding of, hey, are we generally looking at a hotter, drier future or a warmer, wetter future, or maybe different scenarios, different futures say one or the other, and just like think through what that could mean for your utility without doing as detailed or as quantitative of analysis can still provide a lot of value. I'll tee up, I think we're getting a presentation shortly on the EPA SWIFT tool. So I know that is one of a great tool that's available for folks to kind of go through a standardized process to understand some of their vulnerability to natural hazards. I did drop in a link for the Water Utility Climate Alliance in one of my responses. They're another great organization that provides a lot of case studies, some direct work with utilities that you can reach out to. So there are ways that you can use those available data sources, tools, case studies to at least start thinking about some of these questions in a way that you can do with your own staff, to kind of ask yourself what if questions and think about how your utility could respond to that without doing a really detailed, thorough assessment that would typically require greater investment. And that can still add a lot of value.
Mm-hmm. Okay, great. We are at time, but thank you so much for all of that. And please feel free to continue this great discussion that's going on in the chat. So thank you, Lisa and Rachel. We really appreciate you being here today and sharing all your expertise with us.
Thank you. Check out the
Thank
handout.
you.
There's a lot of free manuals and examples and stuff. Yeah.
Yeah, we
Get you
will be
quicker.
thank you, Lisa. So Lisa did, yeah, thank you. Lisa did prepare well, Lisa, why don't you explain real quick in a sentence?
Well, it's just
It's
a whole bunch of links of free documentation and manuals and guides that I think you should have access to easily and quickly. The cost issue was brought up, and appreciate that. There's a lot of really good information. I mean, these manuals, the M71 and M60 are at cost, but there's others out there from FEMA, from EPA, from the AWA Technical Education Council. There's a lot of free reports out there too, publicly.
Okay, great. So we will be sharing that on the shared waters on our workshop website. So thank you for preparing that and providing it. And we'll share it with all the participants or for everybody up on the workshop website. Okay, so before we move on, I do have one quick follow-up question. So we heard a lot of information, I think, at the beginning of the session. People were saying they really weren't that familiar with these manuals, but we're curious to know, after hearing from Rachel and Lisa today, how likely are you to explore either the M71 manual or the M60 manual? Are you very unlikely to explore them further? Unlikely? Unsure if you will explore them further, likely or very likely to explore these manuals further. Um, so it looks so far like people are leaning towards likely and very likely. Okay, thank you for letting us know. Let's move on to our next session, which, as Rachel said, also that was a really good segue thinking about what kind of technical assistance is out there. So we'll be hearing about EPA's SWIFT Technical Assistance Program, as well as a utility case example from Central Lake County Joint Water Action Agency. We will be hearing first about the SWIFT program itself, and then we'll be hearing a case study. Our first speaker is Carrie Michelini. Carrie's a source water protection coordinator in the water division at US EPA's Region 5 office in Chicago. And so with that, Carrie, I will go ahead and turn it over to you.
Great, Margaret. Thanks so much. And yeah, I can imagine after a couple of hours of poring over some rich data resources and some really dense guidance manuals, one might be thinking about, gee, I could use a little help navigating all this great material. And so let's talk a little bit about technical assistance through US EPA's Strengthening Water Infrastructure for Tomorrow initiative, otherwise known as SWIFT. Next slide. Obviously, natural hazards and disasters pose significant challenges to utilities across the country, often resulting in infrastructure damage that can disrupt the flow of critical water, wastewater services to our communities. So SWIFT's mission is to help utilities account for all these risks and make informed infrastructure and investment decisions when recovering from previous disasters or when preparing for the next ones. So we provide direct one-on-one assistance to utilities looking for support with areas such as assessing natural hazard risk and potential impacts to vulnerable assets, identifying mitigation strategies, quantifying the possible risk and reduction in risk that different projects can deliver, and calculating what those projects' return on investment might be. Ultimately, our goal is to help utilities make risk-informed planning decisions that strengthen their ability to handle disasters, leave them with materials that help support both the resilience and business case for new infrastructure funding and investment. We provide free access to all of our hazard maps, risk assessment tools on our website, as well as other resources like utility case studies, relevant federal funding programs, and a variety of news and announcements. You can request free direct technical assistance through our website and register for upcoming webinars and events. Next slide. This technical assistance is under an umbrella of a variety of technical assistance services run out of our Office of Water at US EPA for drinking water, wastewater, and stormwater utilities. This is direct, free, one-on-one support for a host of areas such as cybersecurity, engineering support, and what we're going to focus on now are swift technical assistance, which helps utilities assess their risks to natural hazards and disasters and to find those cost-effective solutions to strengthen their infrastructure and operations against those risks. Next slide, please. So a few reasons why some utilities have been coming to us for assistance lately. Some just want to better understand the risk to hazards such as drought, such as flooding, such as wildfire, and which of those assets might be most vulnerable. Some utilities need help coming up with project ideas that could help strengthen their system against those hazards. Some have projects in mind, but just need help prioritizing which ones they should spend their money on first by identifying which ones provide the greatest risk reduction and return on investment. And some need a good narrative to help justify their projects in funding applications, need to help justify to their boards or ratepayers why they need to spend money on resilience projects and how it will benefit the community in times of emergency. Some need connected to into the funding world to learn more about the different financing options available to them. And as has been mentioned, some just need help updating their risk and resilience assessments or emergency response plans, which are required for drinking water utilities of a certain size under the Safe Drinking Water Act. Next slide. So we have a series of approaches for technical assistance that come to us requesting one-on-one help. These approaches do build on one another. So you can theoretically walk through all of them, or we also can just meet you where you're at. And you get to pick and choose and decide which approaches you want to cover based on the specific needs of your utility. And if you don't know where to start, then we can help you determine the overall scope of the assistance. So starting at the left, we can help utilities evaluate natural hazards and us understanding the risks of those extreme weather events. We can help conduct baseline risk assessments to help utilities calculate their current financial risk to a given natural hazard by using a risk equation that considers threat likelihood, or how likely the hazard is to occur in any given year, with the vulnerability likelihood, which is how susceptible the utility is to the hazard, and the financial consequences, which include the potential financial impacts of the hazard, not only to the utility through damages, but also to the community and to public health as a result of service disruption. We also can go through a cost-benefit analysis to identify projects that enhance the resilience of the system to a given hazard. And then once we've identified those strategies, we can evaluate whether the financial risk to your system would be reduced by implementing your strategy and whether that risk reduction or that potential return on investment would be worth the overall cost to implementing the project. And then we can help provide navigation support, looking at different funding options and other assistance opportunities. Next slide. So here's a kind of a timeline of the types of assistance that typically can play out. It obviously starts with what kind of questions you have. So I encourage you to reach out to us with any questions that you have about your hazard risks. You might be worried about which natural hazards to be concerned about. It could be droughts, it could be floods. We might want to know about resources that exist to understand drought risks. We might want to evaluate different projects that could be implemented to build resilience to your system, and then which of those planned projects are going to most effectively reduce the risk. So it starts with an introductory call. After you reach out to us, we could just set up a quick meeting to evaluate your questions and your risks. We'll determine the technical assistance scope, looking at the range of options from the previous slide. And ultimately, even if we're not a good fit for providing assistance, we may be able to refer you to other types of technical assistance services. If we move forward, then we're typically setting up a handful of virtual meetings, 2 to 3 meetings with up to a couple hours in each, working through all those different evaluation strategies, such as looking at data, looking at a risk assessment, looking at a cost-benefit analysis. These are sessions led by a contracting team with US EPA of experts that we have with us, and we are working around your busy schedule at the utility. And in the end, we provide a final set of materials that you can use for future funding proposals and funding needs. And so we have a variety of options that I think can be tailored to your assistance requests. Next slide. Here's a couple examples of some of the assistance that we provided recently. Spoiler alert on the first one, we're going to hear more from this Illinois utility where we recently have helped evaluate the drought risks to drinking water intakes. And so we'll hear more about that scenario in just a few minutes. But recently we worked with a community down in North Carolina, looking at their stormwater projects that were previously rejected by the FEMA hazard mitigation program for not clearly demonstrating the resilience benefits. And so we can help work through some of that justification when it comes to applying for new funding programs. We also recently worked with the downstate Illinois community, a small community, evaluating their river raw water pump station resilience issues, and it helped evaluate some of the kind of cost benefit options for moving forward with a funding request. Next slide. So on our SWIFT website, we have a whole host of tools and areas for technical assistance requests that you can find. These are all tools that are publicly available that can be used by anybody. But if you need a little extra help, that's where requesting for technical assistance from us comes into play. Next slide. I'll just leave you with this QR code and a URL to where you can go to find the ability to request technical assistance or peruse some of the resources we have with our SWIFT initiative. And I encourage you to reach out to us if you need some help. And I'll be turning it over to my colleague Grant for some local insight into kinds of assistance that has been provided recently.
Great, thank you so much, Carrie. So we, as a reminder, will hold questions for Carrie until the end of the session. I see there are some going into the chat, and we'll take questions for Carrie and Grant at the end of the session. So Grant is our next speaker. Grant has served as the Director of Operations at the Central Lake County Joint Action Water Agency for the past 6 years, providing for the drinking water quantity and quality needs of their member communities. He is a Class A water operator and all-around water geek with 24 years of public service in the water industry. So please join me in welcoming Grant.
Thank you very much, Margaret. I'm very lucky to work for the Central Lake County Joint Action Water Agency, or CLC-JAWA for short. We are a regional drinking water supply, and we serve about 100 square mile service area in Lake County. And our current plant is rated for about 50 million gallons a day of treatment. So we participated in the SWIFT program, technical assistance, this past year to hopefully identify our most vulnerable infrastructure in our system. And I got to say, it was a great experience for me. Getting on the first call was very surprising to see the deep bench that the program has as far as industry professionals and scientists, climatologists, engineers. It was really like a STEM party. Probably the most fun I've had at work in a while, just kind of geeking out with other industry professionals about water. So next slide, please. So something to recall as we go through is our treatment plant has a capacity of 50 million gallons a day, but we're going to be talking about our raw water pump station. So if we have a branched system, meaning we have single branches of water main going out into our system that are single points of failure, and if that branch system is a tree, then our raw water pump station and intake are the roots of that tree. So bottom left picture here is actually our raw water intake. That structure is about 3,000 feet out in the lake. It's buried in the bed of the lake. It transmits water through our 56-inch intake piping. The second picture in the middle on the bottom shows the installation of that piping back in 1992. And you can see that our pump station actually sits up on a bluff next to the lake. It's about 70 feet higher in elevation than the lake itself. So the bottom picture, or the right picture on the bottom, shows actually our raw water wet well being constructed, and they actually had to dig down or excavate 100 feet down from that bluff to get under the lake level for water to flow by gravity through that intake system and into our raw water wet well 100 feet down underneath the building there. So With the SWIFT program, we quickly identified that, if we can't get water from the lake, we can't do anything. So our most vulnerable infrastructure is our intake, our pumping station, really our ability to get water out of the lake. So how climate or hazards might affect that are through drought and heat, which might affect the lake level and the temperature of the lake, which both directly affect our capability of pulling raw water from the lake. Next slide, please. So this is a conglomeration of several drawings of that pump station up on the bluff, and then going down. This is to scale elevation wise, but of course not laterally, because our intake is actually about 3,000 feet long. So it's truncated laterally. So what you can see here is the lake level, max lake level, and minimum lake level in the horizontal blue lines out over our intake structure out in the lake. So how our system is impacted by lake level is the lake level actually provides pressure or head on our system. So as we're drawing water from the wet well to the left of the page, as we draw water from there, the lake level pushes down on our structure and pushes the water into that wet well. So the higher the water level, the more the pressure to begin with, the faster the flow into our wet well. The lower the lake level, the slower the flow, the slower our wet well can rebound. So the less water we can take from the lake. Next slide, please. So I really love this chart on top. This is a drought frequency and how bad it is. Sorry, chart from 2000 to today. And what I really want to focus on are the 2 years of 2013 and 2021. 2013 was one of the lowest lake levels on record, and we believe that it was due to a pretty severe drought, back in 2006 that kind of kept us level. There wasn't really any major drought from 2006 until 2013. But we hadn't seen major rebound in the lake. So 2013, we saw one of the lowest lake levels on record. But you can see after that, there really wasn't any major drought and very infrequent droughts from 2013 till about 2021. And during that time, the lake rebounded. It rebounded so much that we saw one of our highest lake levels in 2021. And that's one of the record lake levels. So after that point, you can see that the drought severity increases and the frequency increases and the lake level drops. So just a quick look at how the correlation between drought and lake level. Next slide, please. So in the next slide, we can see a chart on the left, which was created by our engineers who are doing a capacity study right now. This chart tells us how much water the lake can push into our wet well at different elevations of the lake. So you can see the chart on the right is historical lake levels from NOAA. And so you can see to the right that 2021 high lake level, I think there was another one back in 1985. We would technically be able to pull 66.5 million gallons out of the lake. We can't even treat that. We would never send that much water to our treatment plant because we can only treat 50 million gallons a day, which is the capacity from that first or second slide. So we're good at max level. Historical average, which is around where we are right now, we can pull about 58 million gallons a day. Again, we can't treat it. We're doing really well. The concern is when we're at low lake level. So when we're at historic low lake level, we can only pull about 46 million gallons a day from the lake. So we would not be able to meet our 50 million gallon a day capacity if our demand met that, which it doesn't currently. Currently, our yearly average demand is about 20 million gallons a day. In the summer, we might see 30. But right now we're not at risk of not being able to meet our demand. Next slide, please. So you can see here our plant capacity is 50 million gallons a day. And on the chart, the column to the right shows that 50 million gallons a day, which we would need a lake elevation of 577 feet, which is greater than the historical low. And there are 4 to 6 times just in between 2000 and 2015, where it dropped below that, where we would not have been able to meet capacity or demand during those times if our demand was 50 MGD. So when will we need to address this? Should we be addressing it now? We'll definitely need to address it as our demand increases up into our capacity. Next slide, please. So the SWIFT program really was looking at historical data, but for this presentation, I did want to include this slide, which I pulled from a recent presentation on lake levels. And this is a slide provided by Andrew Gronwald from University of Michigan, among other colleagues that worked on it. And you can see that, they did several, if not hundreds of future modeling of what the lake level might look like. That's the light blue lines in the background on this trend. And then they chose one of those models or futures and put that in the dark blue. And I think if you click one more time, it might put our capacity line on there. So there we go. So the elevations, unfortunately, they're in meters, but the line equals that 577 feet. So you can see there's very likely going to be years in many of these models where the lake level will not allow us to meet that 50 million gallon a day demand if and when we get there. So something we'll have to look at as we go forward. Next slide, please. So that's talking about lake levels due to, potentially due to drought. So next I want to talk about lake temperatures. So I recently read an article about how the Great Lakes are some of the fastest warming lakes in the world. And there were some very drastic graphics and charts on there showing major increases in temperature. And so, of course, I get skeptic anytime I see some sensationalized data and trends. So I went into NOAA and grabbed the daily temperatures for the lake over the last 30 years here. Trended them myself. You can see in the background, the light blue lines is that actual daily data. And it showed what I expected it to. The lake goes up to 70, 75 in the summer, goes down near freezing in the winter. That's not a big surprise. So I trended it, the annual averages in the red. That didn't really show me, at least just to my naked eye, any great increases happening in the lake. But when you throw the trend line on here, the dashed black line, it is obvious that the lake has been warming over the last 31 years, according to this trend, to the tune of 1 to 1.5 degree Fahrenheit every decade. So that's going to impact the temperature in our building and how we can pump the water. And I'll show you what I mean in the next few slides. Next slide, please. So our pump station, down about 60 feet in that station, is our pump room. And we've got 5 pumps here. Usually in the past, we could meet demand by using maybe 2 or maybe 3 pumps at a time. But as demand increases and we have higher, max daily demands, we might see 4 of these running at any time, which creates a lot of heat. And the next slide, if you go to that, shows on the left 2 of our VFDs. Now we have 5 of them. They're all in the same room. We call that room our control room. And as more of those are running, the warmer that room gets. The warmer the room gets, the more those pieces of equipment are impacted by the heat that's generated by them. So currently, we actually cool the entire building with our raw water. So we pump raw water, the picture on the right, we pump raw water through our air handling units. And that cools the air as it flows through those air handling units, cooling the building. keeping this control room at a temperature that's good for the equipment. And if you go to the next slide, we'll look at a trend of the temperature in that room. So the room temperature is in Fahrenheit. It's green on the chart here, and the raw water temperature in yellow is in Celsius, but I've adjusted the scale max in this chart so that you can see the difference accurately. And if you look at it as Fahrenheit, the yellow trend line stays within about 10 degrees Fahrenheit. Um, so that means that the room is staying within 10 degrees of the temperature of the lake. So it's about 10 degrees warmer in that room than the lake is at any time. So if we see, 75 degrees in the lake, which we are seeing, and we're seeing at least more than 70 degrees on more occasions for longer durations. So if this room goes above 85, we need to start cooling it more. And if the lake can't provide that, then we need to find an alternate source of cooling for that room. So that'll be described in the next slide if you go there. This is just a few snippets of the report that we received from Swift after our technical assistance with them. And so they provide recommended countermeasures that would offset the risk and vulnerability created by these natural hazards. So they recommended a new and deeper raw water intake system and a hybrid HVAC system that would allow us to better cool that room. You can see at the bottom here, they provide a cost estimate for what those projects would cost. And the next slide, final slide here, shows the baseline and improved annual threat likelihood and vulnerability likelihood. So you can see on each of these, the threat likelihood doesn't change, but by addressing the hazard, so by putting in a new intake, by improving our HVAC, you can see the vulnerability likelihood goes down significantly. So what we're going to do with this report is take it to our board and see if they're interested in moving up in our CIP the projects that replace or improve these specific parts of our system. So thank you very much for your time, and happy to answer any questions.
Great. Thank you so much, Grant. That was a fantastic presentation. We do have a few minutes for questions for Carrie and Grant. I think I've only seen one come through the chat so far, Carrie. I think someone answered that, which was about, is the create tool still available?
Right, yeah, I see Scarlett from our contractor team responded there. There's been some changes in some of our technical assistance resources under our new administration. So we still provide a variety of different sort of self-assessment and vulnerability tools, and that can be used on your own or through our one-on-one assistance.
Great, thank you for that. And Grant, I see a question that just came in for you, or for both of you. Was any demand forecasting done as part of the project?
Not as part of the project, but we do our own demand forecasting in-house. And right now, for our 2040 max daily demand, we're forecasting, I believe, 40 million gallons a day, max daily demand in 2040.
Okay, another question coming in. Lisa had the same question as Aaron, which was demand forecasting, and also if any demand reduction response called for in recent years was called for when the lake levels are dropping.
As far as reduction response, that I don't know of. That might be something that the Illinois Department of Natural Resources might initiate. But in Illinois, and specifically on Lake Michigan in Illinois, we are regulated by the IDNR according to an allocation. So each of our members gets a dedicated amount of water, and it's their average daily demand that they need to be under on a 3-year revolving average. So as long as they stay under that average daily demand over 3 years, they can take however much water up to that as they need. So I think if they started to exceed that over probably 2 of their 3 years, the IDNR might either make them reduce their what they're taking or require proof that they need a higher allocation is what I think would happen.
Okay. And I know we're coming up against time, but I really, really want to ask you a question, Grant and Carrie, which is like we do seem to have a perception or maybe a myth in the region that Lake Michigan is drought and climate resilient, and we don't have to worry about that. And I think what we heard here today starts to dispel that. And so I think my question is maybe double, like twofold, but like, were there any findings from the SWIFT assessment that surprised your team or changed how you think about Lake Michigan and how other communities might be needing to plan for this? And how do we like so what maybe surprised you, but also I'm interested in like how do we communicate to other communities to help dispel that perception or myth?
Sure. So first, what surprised me, one was, the actual lake temperature increase. So maybe not surprised, but I'm very skeptical on what I deem to be sensationalized climate change data. So I like looking at it in terms that I understand. So it was interesting to see that, yeah, the lake is warming over the past 30 years. And if I extrapolate that in my time here, we're going to have to fix our HVAC system. I was a little surprised that at low lake level we can't get our maximum capacity, treatment capacity, I should say. So that one was interesting to me. It does correlate to the current capacity report that's being put out for us. So something interesting that has happened since talking with our engineer, looking at our capacity report, they have installed or designed an intake for another Lake Michigan water treatment plant, and theirs is 1 foot deeper at its highest point. So something interesting about the lake and our intake, it follows the lake bed up as it comes close to our raw water pump station. So there's kind of like a belly where it comes into the intake, but then it has to travel up with the lake and then drop down into our wet well. If the lake drops lower than that high point in our system, we get zero water. So seeing that, our engineers actually designed in a 1 foot deeper high point in that municipality's intake structure.
Great. Thank you. Thank you so much for sharing that. Thank you, Carrie and Grant. I think that was a great closing presentation for us and really tied together a lot of the issues we heard today. So thank you both for taking the time to be here today.
Thank you.
Okay, so before we wrap up today's workshop, we do have one final Mentimeter question for you. We would like to know, do you think your community or utility could benefit from a swift resilience assessment or technical assistance process of the kind that we just heard about from Carrie and Grant? So please just take a quick moment if you can. I know we're a couple minutes over time, but if you do have time to respond. So yes, your community could benefit. Maybe you're not quite sure yet. You need to hear more. No, you don't think they could benefit, or you're still unsure. Okay, so it looks like we've got some unsure and some yes. And Carrie, I'm assuming folks who are unsure can reach out to you to learn more and as well as visit the website. Okay, so with that, we really hope that today's presentations provided you a lot to think about. We hope that you got some new ideas, tools, and resources to support your community and utilities efforts to prepare for climate variability, drought, and long-term water supply challenges. As a reminder, today's workshop was recorded, so we'll have that recording up and posted on the website as soon as we're able to process it. We'll also have all the presentation materials and additional resources, including that Word document that Lisa so kindly prepared for us with all those resources, but all of the links and everything that you're seeing in the chat, we'll have available for you. So on behalf of Illinois Indiana Sea Grant, CMAP, and our project partners, including our funder, Illinois Department of Natural Resources, we'd like to really thank you all. Sincerely thank all our speakers for sharing their time and expertise, and thank all of you for taking the time to join us today. So thank you, and we hope to see you at a future Shared Water, Shared Futures workshop. We do have 2 more workshops coming up on September 10th, Modernizing Illinois Well Impact Review Process, and then November 12th, Understanding Water Governance and Management. And of course, the recordings of our past workshops are always available for you to go back and revisit, or for those, and if you know anyone who might benefit from those workshops, you can share those recordings with them as well. So thank you. That ends today's workshop.